For centuries, humanity has gazed at the stars, seeking answers to our most profound questions. But with each discovery, we uncover even greater mysteries. From the mind-bending physics of black holes to the possibility of ancient alien visitors, our universe is filled with mysteries that challenge our understanding of reality. Join us as we dive into the most mind-blowing mysteries about the universe. When information, matter, or energy falls into a black hole, we encounter one of the most intriguing paradoxes in modern physics. Imagine a particle carrying detailed information about its properties, such as its position, speed, and unique qualities. As this particle crosses the event horizon, the boundary beyond which nothing can escape, that information seems to vanish from our observable universe. This scenario raises fundamental questions because the laws of quantum mechanics state that information should never be lost. The apparent destruction of information in black holes challenges our understanding of the fundamental nature of reality and the interplay between gravity and quantum mechanics. This apparent contradiction between quantum mechanics and general relativity is known as the information paradox. Stephen Hawking once proposed that information falling into a black hole could be lost forever. But this idea contradicts the principle of quantum determinism, which states that the past and future states of a system should always be determinable from its present state. Recent theories, including developments in string theory and the holographic principle, suggest that information might be preserved in some way. One idea is that information is encoded on the event horizon itself, much like a hologram, preserving the details without actually losing them inside the black hole. Another fascinating notion is the concept of Hawking radiation, where black holes can emit radiation over time and eventually evaporate. Some scientists theorize that information might slowly leak out through this radiation, albeit in a highly scrambled form. This complex interplay between quantum mechanics and general relativity remains one of the deepest mysteries in physics, fueling ongoing research and debate. Each step forward in understanding promises to illuminate not just the nature of black holes, but the foundational workings of the universe. Supermassive black holes, with masses ranging from millions to billions of times that of our Sun, are enigmatic giants residing at the centers of most galaxies. Their formation is still a topic of active research, blending several fascinating theories into a compelling narrative. One prevailing hypothesis posits that these colossal black holes started as smaller, intermediate mass black holes. Over cosmic timescales, they grew by voraciously consuming gas, dust, and even entire stars from their surroundings. This accretion process, combined with mergers between black holes, steadily built up their massive sizes. Imagine an insatiable cosmic entity continuously feasting on anything within its gravitational pull. Another theory suggests that the seeds of supermassive black holes may have formed very early in the universe's history, just a few 100 million years after the Big Bang. In these primordial conditions, giant clouds of gas could have collapsed directly into large black holes, bypassing the usual stellar-sized black hole phase. This process, often referred to as direct collapse, might explain how supermassive black holes appeared so early in the universe. Galaxy mergers also play a significant role in the growth of these black holes. When two galaxies collide, their central black holes can eventually merge, forming an even more massive black hole. The merging of these galaxies often drives large amounts of gas towards the center, providing additional fuel for the black hole to grow rapidly. Across billions of years, these Goliaths of gravity sculpt the galaxies around them, influencing star formation and the dynamics of galactic cores. Understanding their formation not only unravels the mysteries of these cosmic titans, but also provides critical insights into the evolution and structure of the universe. Hawking radiation, proposed by physicist Stephen Hawking in the 1970s, is a groundbreaking concept that combines principles of quantum mechanics with general relativity to explain a previously unimagined phenomenon. Black holes can emit radiation and, over exceedingly long timescales, gradually evaporate. Near the event horizon of a black hole, the boundary beyond which nothing can escape, quantum mechanical effects come into play. According to quantum theory, particle-antiparticle pairs are constantly being created and annihilated throughout space, even in the vacuum around a black hole. Occasionally, these pairs form right at the event horizon. In some instances, due to the intense gravitational forces, one of these particles may fall into the black hole while the other escapes into space. The particle that escapes carries away some energy from the black hole, effectively reducing the black hole's mass. This escaping particle is what we detect as Hawking radiation. Over incredibly long periods, this process causes the black hole to lose mass and energy. As it continues to emit Hawking radiation, it gradually shrinks, a process referred to as black hole evaporation. The full evaporation of a black hole is a slow process. For most black holes, especially the supermassive ones, this occurs over timescales far beyond the current age of the universe. However, for small black holes, the loss of mass can speed up dramatically as they get smaller, leading to a final burst of radiation before they vanish entirely. Hawking radiation not only provides a mechanism for black hole evaporation, but also bridges the gap between quantum mechanics and Einstein's theory of general relativity. It serves as a step towards understanding the deeper connections between the laws governing the tiniest particles and the largest structures in the cosmos. The idea of harnessing energy from rotating black holes is not merely the stuff of science fiction, but is grounded in fascinating theoretical physics. Rotating black holes, also known as Kerr black holes, possess an enormous amount of angular momentum and gravitational energy. This seeming paradox of tapping into a black hole's immense power was first proposed by physicist Roger Penrose in the form of the Penrose process. The Penrose process involves a particle entering the ergosphere, a region just outside the event horizon of a rotating black hole where space-time is dragged around at astonishing speeds. Within the ergosphere, it is theoretically possible to split the particle into two. One part falls into the black hole while the other escapes, carrying off more energy than the original particle had. In doing so, the process extracts a fraction of the black hole's rotational energy. Another fascinating concept is the Blandford-Xenarjek process. This theory suggests that magnetic fields surrounding a black hole could interact with its rotation, channeling energy out in the form of powerful electromagnetic radiation, jets of high-energy particles, often observed emanating from the regions around supermassive black holes at the centers of galaxies, could be an indication of such energy extraction mechanisms at work. These theoretical methods present tantalizing possibilities but come with immense practical challenges. The extreme conditions and immense scales involved make actual energy extraction a daunting, if not currently impossible, engineering feat. Nonetheless, studying these processes enriches our understanding of black hole physics and the incredible forces at play at the edges of our scientific comprehension. While we may be far from building black hole power plants, these ideas stretch the boundaries of what we consider possible, propelling us towards deeper inquiries into the universe's most enigmatic entities. Whether or not we can ever directly harness this energy, the principles behind these processes continue to offer profound insights into the nature of space, time, and gravity. Should you find yourself falling into a black hole, your experience would depend greatly on the black hole's size and mass. For a stellar mass black hole, typically about several times the mass of our Sun, the journey would be extraordinarily violent and brief. However, falling into a supermassive black hole, millions or billions of times the mass of the Sun, could provide a longer, though equally unsettling, trip. As you approach the event horizon, the point of no return, the effects of gravity become extreme. For a stellar mass black hole, tidal forces, extreme differences in gravitational pull, would stretch and compress your body in a process whimsically called spaghettification. You would be elongated along the direction of the black hole's pull while being compressed along the other directions, quickly leading to your demise before you even reached the event horizon. In contrast, if you fell into a supermassive black hole, the longer distance to the singularity at its core means tidal forces at the event horizon would be less intense. You could theoretically pass the event horizon without immediate catastrophic spaghettification. As you fall deeper into the black hole, the view to the outside universe would shrink to a small, bright spot directly overhead, slowly fading as you approach the singularity where gravity crushes all matter infinitely small. Once inside the event horizon, the laws of physics as we understand them break down. Theories suggest time and space become interchangeable, leading to speculations about what might occur. Some suggest you could encounter the singularity where the matter is crushed to an infinitely dense point, ending your journey. Others hypothesize the possibility of reaching a region where space-time could connect to another part of the universe through hypothetical constructs called wormholes, or Einstein-Rosen bridges. Whether the final moments involve a rendezvous with a singularity or passage through exotic cosmic pathways, falling into a black hole remains a mysterious and perilously final voyage, an exploration on the very edge of our scientific understanding. Detecting exoplanets, the planets that orbit stars beyond our solar system, involves several ingenious methods, each leveraging different aspects of astronomy to unveil these hidden worlds. One of the most successful and widely used techniques is the transit method. When an exoplanet passes directly between its parent star and us, it causes a slight periodic dimming of the star's light. By carefully monitoring and measuring these dips in brightness, astronomers can infer the presence of an exoplanet, its size, and even some clues about its atmosphere. Another powerful method is the radial velocity, or Doppler technique. This approach relies on detecting tiny wobbles in a star's position caused by the gravitational pull of an orbiting exoplanet. As the planet orbits, it tugs on the star, causing it to move slightly towards and away from us. This motion shifts the star's light spectrum towards the blue end when it moves towards us and towards the red end when it moves away. By studying these spectral shifts, scientists can estimate the exoplanet's mass and its orbital period. The direct imaging method, though challenging, involves capturing actual images of exoplanets by blocking out the overwhelming glare of their parent stars. Using advanced instruments and techniques like coronagraphs or star shades, astronomers can isolate the faint light reflected or emitted by the exoplanet. This method is particularly useful for studying larger exoplanets that are relatively far from their stars, in regions where the contrast between the planet and starlight is less blinding. Another intriguing approach is gravitational microlensing, which takes advantage of the warping of space-time caused by a massive object, such as a star or planet, passing in front of a more distant star. The gravity of the intervening object acts like a lens, magnifying the background star's light in a specific pattern. If an exoplanet is part of the intervening system, its presence can be inferred from the distinct characteristics of the light curve. These methods, often used in combination, have led to the discovery of thousands of exoplanets, painting a diverse and fascinating picture of planetary systems far beyond our own. With each detection, our understanding of the universe expands, revealing the potential for worlds that might harbor life or offer conditions vastly different from those we know. Super-Earths are a class of exoplanets with masses larger than Earth, but significantly less than those of ice giants like Uranus and Neptune. Typically, super-Earths boast masses ranging from about 1 to 10 times that of Earth. Their unique position in the planetary spectrum has captivated scientists, as they offer a window into diverse planetary formation and compositions. One reason super-Earths intrigue scientists is their potential similarity to Earth, which raises questions about their habitability. Many super-Earths lie within their star's habitable zone, the region where conditions might allow for liquid water to exist on the planet's surface. Water is a key ingredient for life as we know it, making these planets prime candidates in the search for extraterrestrial life. The composition of super-Earths can vary widely, from rocky planets with thin atmospheres to water worlds with deep global oceans. Studying super-Earths also broadens our understanding of planetary formation. Our solar system lacks planets with masses between Earth and Neptune, so discovering and studying super-Earths in other systems helps fill in gaps in our knowledge. These planets might represent a common step in planetary evolution, providing clues on why certain planetary systems evolve differently. Some super-Earths have intriguing atmospheric compositions, detected by analyzing the starlight that filters through their atmospheres during transits. This spectrum can reveal the presence of gases like hydrogen, helium, and potentially even more complex molecules. By studying these atmospheres, scientists hope to learn about the processes shaping these worlds, including volcanic activity, weather patterns, and potential biosignatures. Super-Earths embody a diverse array of worlds, each with the potential to challenge and expand our definitions of habitability and planetary formation. As our detection methods and technologies improve, the study of these planets will undoubtedly yield more surprises, deepening our understanding of the myriad possibilities within our universe. Rogue planets, or nomadic planets, wander through the galaxy unbound by any star. These mysterious worlds, existing in the dark expanse between stars, raise fascinating questions about the potential for life in such isolated environments. While the absence of a parent star presents significant challenges for sustaining life as we know it, certain theoretical scenarios suggest it might not be entirely out of the question. First, let's consider the possibility of subsurface oceans. If a rogue planet retains enough internal heat from its formation or experiences tidal heating from interactions with a large moon, it might possess a subsurface ocean insulated by a thick layer of ice. Similar to the icy moons of Jupiter and Saturn in our solar system, such oceans could potentially harbor microbial life or even more complex organisms, exploiting the energy from hydrothermal vents at the ocean floor. Another intriguing scenario involves thick atmospheres. If a rogue planet has a dense atmosphere rich in hydrogen or other insulating gases, it could trap enough heat to maintain liquid water on its surface or beneath a layer of ice. This atmospheric blanket would act like a giant thermos, retaining geothermal heat and potentially providing conditions suitable for life. This concept of atmospheric insulation expands the possible habitable zones far beyond the confines of starlight. Life may also arise from different biological principles than those on Earth. In the absence of sunlight, alternative energy sources, such as chemical energy from the planet's interior, might serve as the basis for an entirely different kind of biosphere. Extremophiles on Earth, microorganisms that thrive in harsh environments like deep-sea vents and acidic hot springs, hint at life's remarkable adaptability to diverse energy sources and conditions. Rogue planets push the boundaries of our understanding of habitability and challenge our perceptions of where life could exist. While the conditions are undoubtedly extreme, the resilience of life on Earth in similarly harsh environments suggests that life on rogue planets, though speculative, remains a tantalizing possibility. As our knowledge and detection techniques advance, these lonely wanderers might one day reveal themselves as harboring the secrets to life's adaptability beyond the stellar neighborhoods we are accustomed to. Searching for biosignatures on exoplanets involves using sophisticated techniques and instruments to detect chemical and physical signs of life from light years away. These biosignatures are essentially the indicators of biological processes that can be observed and measured from Earth or orbiting space telescopes. The quest for these telltale signs is one of the most exciting frontiers in modern astronomy and astrobiology. One primary method is the analysis of exoplanetary atmospheres, which can be done during transits. When an exoplanet passes in front of its host star, a small fraction of the star's light filters through the planet's atmosphere. By examining this light with tools like spectrometers, scientists can identify the absorption lines corresponding to specific gases. Certain gases, such as oxygen, methane, or ozone in particular, concentrations might indicate biological activity. For instance, on Earth, a combination of oxygen and methane in the atmosphere is mostly produced by life. Another approach involves the study of reflected light from an exoplanet, known as direct imaging. Instruments use advanced techniques to block the overwhelming light from the parent star, allowing astronomers to analyze the spectrum of light directly reflected off the planet's surface or atmosphere. Reflected light can reveal various surface materials and atmospheric components. Detection of unusual surface compositions, like chlorophyll-like signatures which on Earth are associated with photosynthesis, might provide clues about potential life. Additionally, scientists consider the possibility of detecting technosignatures, which are signs of advanced technology. These might include unusually structured light patterns or radio signals, akin to those our technology emits. Though the search for technosignatures is more speculative and challenging, the potential discovery of such signals would be a groundbreaking indication of intelligent life elsewhere. Groundbreaking missions like the Kepler Space Telescope and the James Webb Space Telescope, along with upcoming projects, utilize these methods to systematically explore exoplanets' atmospheres and surfaces. As our technological capabilities grow, so does our ability to detect subtle signs of life, pushing us ever closer to answering the age-old question, are we alone in the universe? With each advancement, The dream of discovering life beyond Earth moves from the realm of speculation to the cusp of scientific reality, making the search for biosignatures an exhilarating journey into the unknown. The Fermi paradox is a fascinating puzzle named after physicist Enrico Fermi, who famously asked, "Where is everybody?" This question encapsulates the seeming contradiction between the high probability of extraterrestrial civilizations existing elsewhere in the Milky Way galaxy and the lack of evidence or contact with such civilizations. Given the vast number of stars and potentially habitable planets, Fermi's simple yet profound query continues to perplex scientists and stimulate intriguing hypotheses. One of the central tenets of Fermi's paradox lies in the Drake equation, which estimates the number of active, communicative extraterrestrial civilizations in our galaxy. Factors such as the vast number of stars, many of which have planets in habitable zones, suggest that, statistically, intelligent life should be relatively common. Our Milky Way alone contains around 100 billion stars, many of which are orbited by planets that could host life. Yet, despite the seemingly favorable conditions, we have no conclusive evidence of extraterrestrial civilizations. Several theories attempt to explain this paradox. One idea is the possibility of the Great Filter, a hypothetical stage in the evolution of life that is extremely unlikely or difficult to overcome. This filter could be behind, meaning life rarely evolves to complex organisms, or ahead, suggesting advanced civilizations self-destruct before achieving interstellar communication. Either scenario presents sobering implications for our own civilization's future. Another hypothesis is the concept of the zoo hypothesis, where advanced extraterrestrial civilizations deliberately avoid contact with us, observing humanity from afar like animals in a zoo. They might be waiting for us to reach a certain level of technological or ethical maturity before making contact. Others propose that interstellar travel or communication might be inherently difficult or resource-intensive, limiting the spread or detectability of advanced civilizations. Additionally, some suggest that we might not be recognizing the evidence of extraterrestrial life because it differs significantly from our expectations. Life forms might be so alien in form and function that we fail to perceive their presence. The Fermi paradox remains a profound and open-ended question, driving both scientific inquiry and speculative thought. Each proposed solution, whether it leans towards biological, technological, or sociological explanations, brings us closer to understanding our place in the cosmos and the potential for others sharing it with us. The Great Attractor is a gravitational anomaly in intergalactic space that exerts a powerful pull on the galaxies in its vicinity, including our own Milky Way. Located roughly 150 to 250 million light-years away in the direction of the constellation Centaurus, this mysterious region is part of what's known as the Laniakea supercluster, a massive collection of over 100,000 galaxies bound together by gravity. The intrigue surrounding the Great Attractor arises from its immense gravitational influence. This gravity well is drawing galaxies towards it at velocities of up to several hundred kilometers per second. Observations indicate that entire clusters of galaxies are being pulled towards this enigmatic point. Even our local group of galaxies, which includes the Milky Way, is moving towards the Great Attractor at approximately 600 kilometers per second. Determining precisely what constitutes the Great Attractor is challenging because it lies within the zone of avoidance, an area of the sky obscured by the dense plane of our Milky Way galaxy filled with stars, dust, and gas. This obscuration makes direct observation difficult. However, advanced observational techniques and the use of X-ray astronomy have allowed astronomers to partially peer through this dense foreground. Research suggests that the Great Attractor is likely a major supercluster structure with large concentrations of galaxies, dark matter, and hot gas contributing to its intense gravitational field. One key structure associated with the Great Attractor is the Norma cluster, a massive cluster of galaxies situated near the center of this gravitational anomaly. Nonetheless, the full extent of what comprises the Great Attractor remains an active area of research. Understanding the Great Attractor not only helps us comprehend the motion of galaxies within our local cosmic neighborhood, but also provides insight into the large-scale structure of the universe. This region of space exemplifies the complex gravitational interactions that shape the cosmos, influencing the movement and distribution of galaxies across vast distances. Cosmic voids are vast, relatively empty regions in the universe, devoid of much of the matter that makes up galaxies, stars, and other celestial structures. These voids, some spanning hundreds of millions of light-years across, form an integral part of the large-scale structure of the universe, often described as a cosmic web of filaments and clusters, with the voids as the spacious gaps in between. The formation of cosmic voids is closely tied to the evolution of the universe itself. Following the Big Bang, the universe was initially a nearly uniform soup of particles and energy. Over time, slight quantum fluctuations in this primordial matter density grew due to gravitational attraction. Regions with slightly higher densities attracted more matter, forming galaxies and clusters. Meanwhile, less dense regions lost their matter to these denser regions, expanding into the vast voids we observe today. This process, governed by gravity and the expansion of the universe, has been ongoing for billions of years. Inside these cosmic voids, things are not entirely empty. Instead, they contain very low-density gas, some dark matter, and a sparse population of galaxies and galaxy clusters. The average density of galaxies in these voids is significantly lower than in the more densely populated filamentary structures. The galaxies found within voids tend to be smaller, less luminous, and often isolated compared to those in richer environments. These conditions can lead to different evolutionary paths for galaxies within voids, making these regions intriguing subjects for studying galaxy formation and evolution distinct from denser cosmic areas. Additionally, cosmic voids offer unique opportunities to study dark energy, the mysterious force driving the accelerated expansion of the universe. Since these voids represent underdense regions, they react more sensitively to dark energy, making them excellent natural laboratories for probing its properties. Cosmic voids, while seemingly empty, are rich with information about the universe's formation, the distribution of galaxies, and the enigmatic nature of dark energy. Their study continues to deepen our understanding of the universe's large-scale structure and the forces shaping its evolution. Galaxy filaments are colossal, thread-like structures composed of galaxies, gas, and dark matter, forming the backbone of the large-scale structure of the universe. These filaments can extend across hundreds of millions of light-years, connecting clusters and superclusters of galaxies into a vast, intricate cosmic web. They're among the largest known structures in the universe and play a fundamental role in its overall architecture. The formation of galaxy filaments began soon after the Big Bang. In the early universe, slight density fluctuations in the primordial matter distribution acted under the influence of gravity, pulling matter together into increasingly complex structures. As gravity continued to pull matter into denser regions, long, thin filaments emerged, linking galaxy clusters and sprawling across the cosmos. This process of structure formation is heavily influenced by dark matter, which, though invisible, constitutes the scaffolding around which ordinary, visible matter congregates. Within these filaments, galaxies are not randomly scattered but follow the dense trails created by dark matter. The movement of galaxies along these filaments is driven by gravitational forces, continually funneling matter towards dense nodes where galaxy clusters reside. These nodes, in turn, can merge to form even larger structures known as superclusters. The interactions within filaments also play a critical role in the evolution and formation of galaxies, as their gravitational pull can induce galaxy mergers and trigger new waves of star formation. The study of galaxy filaments provides essential insights into understanding the large-scale structure of the universe and its composition. By mapping these filaments, astronomers can trace the distribution of dark matter, as its gravitational influence is the primary force shaping these cosmic strands. Additionally, examining the properties and dynamics of galaxies within filaments helps scientists explore galactic evolution within different cosmic environments. Galaxy filaments are a testament to the universe's impressive scale and complexity. They illustrate how cosmic forces orchestrate the distribution of matter on grand scales, leading to the rich tapestry of galaxy clusters, superclusters, and voids that define our cosmos. These filaments not only help us grasp the universe's architecture, but also reveal the intricate dance of matter and gravity that continues to shape the cosmic landscape. Galactic superclusters are among the most massive and monumental structures in the universe, comprising tens of thousands of galaxies stretched across hundreds of millions of light-years. Their formation and evolution are a testament to the power of gravity over grand cosmic timescales, starting from the earliest moments following the Big Bang to the present day. The journey of supercluster formation begins with the tiny density fluctuations in the primordial matter distribution of the early universe. These fluctuations, remnants of quantum variances from the earliest moments of the Big Bang, were slightly denser regions of matter spread throughout the otherwise uniform universe. Under the influence of gravity, these denser regions began to attract more matter, slowly evolving into larger structures over billions of years. As these structures grew, they formed dense knots of matter known as galaxy clusters, interconnected by somewhat less dense thread-like structures called galaxy filaments. Clusters and filaments subjected to the persistent gravitational pull of these dense regions first formed groups and then larger associations. Over time, multiple clusters merged into more significant formations, resulting in the extensive superclusters we observe today. The evolution of galactic superclusters involves complex dynamic processes. Galaxy clusters within superclusters continue to move under mutual gravitational attraction, occasionally colliding and merging to form even more massive and denser clusters. These interactions can spur new waves of star formation, alter the shapes and properties of galaxies, and drive the growth of supermassive black holes at the centers of galaxies. Additionally, the ongoing expansion of the universe influences the evolution of superclusters, with some structures becoming more isolated as the space between them stretches. Today, we map these vast structures using tools like large-scale galaxy surveys, which provide a 3D view of the universe, revealing the intricate web of clusters, filaments, and voids. Superclusters like the Virgo supercluster, which includes our own Milky Way, and the massive Laniakea supercluster highlight the grand scale of cosmic architecture. The study of superclusters not only deepens our understanding of the universe's large-scale structure, but also provides crucial insights into the interplay of dark matter and dark energy in shaping cosmic evolution. By observing these colossal structures, we gather valuable clues about the nature of the universe itself, from its genesis to its ultimate fate. Dark flow is a mysterious and peculiar phenomenon observed in the large-scale motion of galaxy clusters. Despite the general agreement that the universe's expansion should be uniform, some galaxy clusters appear to be moving in a specific coherent direction, different from the pattern expected. This movement is not accounted for by the standard cosmological model, which includes dark energy and dark matter comprehensively explaining the universe's observed behavior. Scientists first noticed dark flow when studying the cosmic microwave background radiation, the afterglow of the Big Bang, and observed that certain galaxy clusters moved towards a specific part of the sky. This motion seemed beyond what could be explained by gravitational influences from known structures such as superclusters or filamentary networks of galaxies within the observable universe. The existence of dark flow suggests that there might be influences beyond the observable universe causing these motions. It raises questions about the limits of our current cosmological models and potentially hints at structures or effects outside our cosmic horizon, the furthest distance from which light has had time to reach us since the beginning of the universe. Some scientists speculate that this could imply the presence of massive structures, or even other universes whose gravitational pull affects our own observable universe. This enigmatic movement challenges our understanding because it pushes the boundaries of known physics and forces us to consider that the cosmos might be even more vast and complex than we currently comprehend. Exploring this further could lead to groundbreaking insights about the universe's fabric, its origins, and the potential existence of multiversal realms. By addressing these mysteries, cosmology is driven to think boldly, expanding our comprehension of everything that lies beyond our cosmic line of sight. Hypernovae are extraordinarily powerful stellar explosions, far more energetic than typical supernovae. They result from the collapse of massive stars, generally at least 30 times the mass of our Sun. When such a colossal star exhausts its nuclear fuel, its core collapses under gravity's immense force, leading to a cataclysmic release of energy. A primary characteristic distinguishing hypernovae from regular supernovae is their immense energy output. While supernovae release an astounding amount of energy, hypernovae can be 10 to 100 times more powerful. The underlying mechanisms for this heightened energy relate to the star's mass and the nature of its collapse. In a hypernova, the core's collapse may result in the formation of a black hole rather than a neutron star, as is common in many supernovae. Hypernovae also exhibit unique features in their emissions. For instance, they are often associated with long-duration gamma-ray bursts, some of the brightest electromagnetic events in the universe. These bursts are thought to arise from jets of particles moving at nearly the speed of light, emanating from the star's poles as it collapses into a black hole. This jet formation requires very specific conditions, typically found in the most massive stars with rapid rotation. Another difference is their impact on the cosmos. Hypernovae play a crucial role in seeding the universe with heavy elements. During these colossal explosions, elements heavier than iron are forged and dispersed into the surrounding space. This distribution aids in the creation of future stars and planetary systems, embedding hypernovae as pivotal agents in the cosmic cycle of matter and energy. While supernovae also contribute to this process, the sheer scale at which hypernovae do so is significantly greater, ensuring their indelible mark on the universe's evolutionary tapestry. Magnetars generate the most powerful magnetic fields in the universe through processes initiated during their birth from certain types of supernova explosions. When a massive star, typically around 10 to 25 times the mass of our Sun, exhausts its nuclear fuel, the resulting core collapse often forms a neutron star. However, if conditions during the collapse are just right, particularly involving the star's core rotation and magnetic alignment, a magnetar can be born. In a magnetar, the collapsing core's rapid spin and the intense compression of magnetic field lines significantly amplify the magnetic field strength. This amplification can be up to a quadrillion times stronger than Earth's magnetic field. Essentially, the star's magnetic field lines are tightly wound as the core shrinks dramatically in size, concentrating the magnetic energy into a far smaller volume. The extreme density and pressure inside a magnetar also contribute to the intense magnetic fields. The particles within the core, primarily neutrons, align in such a way that their magnetic moments reinforce each other rather than cancelling out as they do in less dense conditions. This collective alignment magnifies the overall magnetic effect across the neutron star. Magnetars are distinguished by their highly unstable magnetic fields, which can cause dramatic and violent effects on their surfaces. These magnetic instabilities lead to starquakes and the release of enormous bursts of X-rays and gamma rays. These bursts are so powerful that they can affect satellites and even Earth's atmosphere, despite happening thousands or even millions of light years away. These cataclysmic energies and magnetic forces ensure that magnetars stand as some of the universe's most extraordinary and enigmatic objects. Fast radio bursts, or FRBs, are brief, intense flashes of radio waves that originate from far beyond our galaxy. These bursts last only milliseconds, but release an immense amount of energy comparable to what our Sun emits over several days. The mysterious nature of their origins has captivated astronomers since the first one was discovered in 2007. One leading hypothesis is that FRBs are caused by highly magnetized neutron stars known as magnetars. As mentioned earlier, magnetars possess incredibly powerful magnetic fields, and these fields can sometimes undergo sudden changes. These magnetar starquakes or other magnetic instabilities might produce the rapid bursts of energy that we detect as FRBs. Some FRBs have been traced back to regions in space where massive stars often end their lives, lending support to this theory. Another potential source of FRBs is the collision or merging of compact objects such as neutron stars or black holes. When these dense stellar remnants collide, they can create shockwaves and potentially emit these powerful radio bursts. The rare nature of such collisions matches the observed scarcity and randomness of FRBs, making this a plausible explanation for at least some of the bursts. Interestingly, some FRBs repeat, providing further clues to their nature. The repeating nature suggests that the same source can produce multiple bursts over time, which contrasts with cataclysmic events like collisions that happen only once. This observation has led to theories involving objects with continuous emissions, like rotating neutron stars in binary systems or interactions between a magnetar and its surrounding environment. While our understanding of FRBs is still evolving, each new discovery adds pieces to the complex puzzle of their origins. As we improve our detection abilities and gather more data, we hope to unravel the enigmatic nature of these extraordinary cosmic phenomena. Binary star systems consist of two stars orbiting a common center of mass, and their evolution and interaction can be profoundly different from that of solitary stars. The dynamics within these systems lead to unique behaviors and phenomena that are fascinating to astronomers. Initially, when both stars in a binary system are relatively young and still on the main sequence, they interact primarily through gravitational influence. Each star orbits the system's common center of mass, a point determined by their respective masses. If the two stars are close, gravitational interactions can become quite complex. These interactions can cause changes in their orbits and in some cases result in mass transfer where one star pulls material from its companion. But as these stars age, they exhaust their nuclear fuel and evolve away from the main sequence. The more massive star evolves faster, typically becoming a red giant first. As it expands, its outer layers may overflow its Roche lobe, an imaginary teardrop-shaped region around each star where material is gravitationally bound to that star. When this occurs, material can transfer to the companion star. This mass transfer significantly alters the evolution of both stars, potentially spinning up the receiving star and affecting its stellar life cycle. In some cases, this mass transfer can lead to dramatic phenomena. For instance, if the donor star sheds its outer layers rapidly enough, it might become a white dwarf. The accreting star might gain enough mass to experience increased nuclear activity or even explode as a supernova if it surpasses critical mass thresholds. Additionally, if the stars in the binary system are close enough, they might eventually merge, leading to further stellar cataclysms and potentially forming a new single massive star or a neutron star. Binary interactions can also lead to the production of exotic objects, such as X-ray binaries or millisecond pulsars. In X-ray binaries, the compact remnant of one star, such as a neutron star or a black hole, accretes matter from a companion star, emitting intense X-rays. Millisecond pulsars, on the other hand, are neutron stars that have been spun up by accreting material from a companion, rotating hundreds of times per second. Overall, the interplay between stars in binary systems showcases nature's complexity, leading to some of the most energetic and exotic phenomena in the universe, continually reshaping our understanding of stellar evolution and interaction. Quark stars are hypothetical celestial objects which represent an extreme state of matter. They are thought to form under conditions even more extreme than those that create neutron stars. Essentially, a quark star would be formed if a neutron star's core density surpassed a critical threshold, causing neutrons to break down into their constituent particles known as quarks. When a massive star exhausts its nuclear fuel, it undergoes a supernova explosion, often leaving behind a dense core. Typically, if the remaining core's mass is sufficient, it will collapse into a neutron star, where matter is compressed to a state where neutrons are densely packed together. However, if the mass and pressure exceed a certain limit, it is theorized that these neutrons themselves could decompose into quarks, resulting in a quark star. These quark stars would be composed of quark matter, a substance theorized to be denser than neutronium, the matter found in neutron stars. There are two primary types of quarks thought to make up this ultra-dense matter: up quarks and down quarks, which constitute neutrons, along with possible strange quarks, creating what is sometimes referred to as strange matter. This state of matter is so compact that it would have a bizarre property. Any additional matter falling onto a quark star would be immediately integrated into the quark matter, contributing little to increasing the star's size. Observationally distinguishing quark stars from neutron stars poses a significant challenge. as both types of stars would exhibit similar characteristics. However, if quark stars exist, they might display slightly different mass and size relationships, known as mass-radius relationships, compared to neutron stars. They may also exhibit unique cooling patterns or emit bursts of energy detectable by astronomical instruments. The existence of quark stars remains hypothetical, yet the concept pushes the boundaries of our understanding of particle physics and stellar evolution. Confirming the existence of quark stars would not only provide insights into the behavior of matter under extreme conditions, but also deepen our grasp of the fundamental forces shaping the universe. The evidence for the existence of dark matter is drawn from various astronomical observations that reveal discrepancies between the predicted and observed behavior of cosmic structures. One of the earliest and most compelling pieces of evidence comes from the study of galaxy rotation curves. When astronomers, including Vera Rubin in the 1970s, measured the rotation speeds of stars in galaxies, they found that stars at the outer edges rotated just as quickly as those near the center. According to Newtonian mechanics, the stars further from the center should rotate more slowly unless there is additional unseen mass providing gravitational pull. This suggests the presence of an unseen or dark matter component. Another significant source of evidence comes from the phenomenon known as gravitational lensing, where light from distant galaxies is bent around massive objects like galaxy clusters. The degree of bending observed cannot be accounted for solely by the visible matter in these clusters. Instead, it indicates that there is much more mass present, exerting the gravitational forces necessary to curve the light to the extent observed. The cosmic microwave background radiation, the afterglow of the Big Bang, also provides clues. Measurements taken by satellites such as the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft reveal subtle temperature fluctuations in this ancient radiation. By analyzing these fluctuations and the distribution of galaxies in the universe, cosmologists can infer the total amount of matter and energy. The results indicate that only about 1/6 of this matter is the regular baryonic matter we can see and interact with. The rest is dark matter. Finally, observations of galaxy cluster movements offer additional evidence. One famous example is the Bullet cluster, where two galaxy clusters collided. The collision separated the dark matter from the normal matter, producing distinct gravitational effects observable through gravitational lensing. The visible matter, predominantly gas, slowed down and collided, whereas the dark matter continued largely unimpeded. This separation provided a clear picture of dark matter's presence and its different physical properties compared to normal matter. All these observations collectively build a strong case for dark matter's existence. Despite being invisible and not interacting with electromagnetic forces, dark matter's gravitational influence is critical in shaping the structure and evolution of the universe. Its detection remains one of the most exciting frontiers in modern astrophysics and cosmology, with experiments ongoing both in space and on Earth to directly detect dark matter particles. Dark energy is a mysterious and pervasive force believed to be responsible for the accelerating expansion of the universe. Discovered in the late 1990s through observations of distant Type Ia supernovae, dark energy is thought to make up about 2/3 of the total energy density of the universe. Its properties and behavior remain among the biggest questions in cosmology. One way to conceptualize dark energy is through a term in Einstein's equations of general relativity known as the cosmological constant, often symbolized by the Greek letter lambda. This constant can be thought of as an inherent energy of empty space, which exerts a repulsive force counteracting the gravitational pull of matter. As the universe expands, more space is created, and with it more dark energy. This amplifies the repulsive effect, leading to an accelerating expansion. Another perspective is that dark energy could be a dynamic field, similar to but distinct from gravity, dubbed quintessence. Unlike the static energy of the cosmological constant, quintessence would evolve over time, changing the rate at which the universe expands. This viewpoint allows for more complex models and could potentially explain the observed variations in the acceleration rate more flexibly. Dark energy's effects are not immediately noticeable on small scales, such as within galaxies or even galaxy clusters, where gravitational forces dominate. However, on the cosmic scale, its influence becomes profound. The accelerated expansion was confirmed through various means, including the study of the cosmic microwave background radiation and large-scale galaxy surveys, which show that galaxies are moving away from each other more rapidly over time. 2. Current and future observational projects like the Euclid satellite mission and the Vera C. Rubin Observatory aim to map the distribution of galaxies and measure the expansion rate of the universe with unprecedented precision. By examining the large-scale structure of the cosmos and the behavior of dark energy over time, scientists hope to uncover its nature, potentially leading to groundbreaking discoveries that could reshape our understanding of physics and the universe. The intriguing possibility that dark matter might be composed of primordial black holes has garnered considerable interest among scientists. Primordial black holes are hypothetical objects that could have formed in the very early universe shortly after the Big Bang due to high-density fluctuations. Unlike typical black holes, which form from the collapse of massive stars, primordial black holes could be much smaller and represent an entirely different origin of dark matter. One point in favor of this hypothesis is that primordial black holes naturally exhibit many characteristics expected of dark matter. They are massive and do not emit light, fitting the profile of the elusive dark matter that influences the gravitational dynamics of galaxies and galaxy clusters. However, several constraints challenge this theory. Observations of gravitational lensing, where light from distant stars and galaxies is bent by a massive object, have not detected the expected number of lensing events that primordial black holes would cause if they were present in sufficient quantities to account for all dark matter. This places a significant limitation on their possible abundance and distribution. Additionally, primordial black holes of intermediate mass ranges might emit detectable levels of Hawking radiation, or could lead to specific observable effects, such as interactions with stars and gas clouds, which we have not witnessed to match the required abundance for dark matter. Constraints from cosmic microwave background radiation also indicate that the contribution of primordial black holes to the total dark matter content must be small. Despite these challenges, the idea has not been entirely ruled out. Recent developments in astrophysics and gravitational wave astronomy, particularly those from the LIGO and Virgo collaborations detecting mergers of black holes, have revived interest in the possibility of primordial black holes. Some of these mergers involve black holes of masses and frequencies that might be consistent with primordial origins. Ongoing and future observational efforts aim to explore various mass ranges and properties of primordial black holes more comprehensively. While we continue to seek direct evidence for dark matter particles and alternative explanations, the primordial black hole hypothesis remains an intriguing possibility that could, if proven, offer revolutionary insights into both dark matter and the formation of the early universe. Weakly interacting massive particles, commonly known as WIMPs, are among the leading candidates to explain the elusive nature of dark matter. These hypothetical particles are thought to have significant mass and interact only through the weak nuclear force and gravity, making them extraordinarily difficult to detect. The concept of WIMPs emerges naturally from extensions to the standard model of particle physics, such as supersymmetry, which posits the existence of heavier counterparts to known particles. One of these potential particles could be a WIMP, possessing the right properties to account for the observed effects of dark matter on the cosmic scale. One key reason WIMPs are considered viable dark matter candidates is the so-called WIMP miracle. When scientists calculate how WIMPs would have behaved in the early universe, they find that particles with the right mass and weak interaction properties would have naturally resulted in an abundance consistent with the observed density of dark matter today. This elegant coincidence strengthens the case for WIMPs as dark matter constituents. Detecting WIMPs directly involves several experimental approaches. Direct detection experiments, such as those conducted with large underground detectors filled with supercooled noble gases like xenon or argon, aim to spot the rare interactions between WIMPs and atomic nuclei. These interactions would produce tiny signals of light or heat, which researchers analyzed to determine if they match the expected profile of WIMP interactions. Indirect detection methods focus on looking for the byproducts of WIMP annihilations or decays. If WIMPs collide, they might annihilate each other and produce gamma rays, neutrinos, or other particles that can be detected by instruments like the Fermi Gamma Ray Space Telescope. Lastly, particle accelerators like the Large Hadron Collider seek to create WIMPs by colliding protons at incredibly high energies. By examining the debris from these collisions, scientists hope to spot missing energy or momentum signatures indicative of WIMPs. While WIMPs have yet to be detected, ongoing research and technological advancements continue to push the boundaries, offering hope that we might eventually identify these elusive particles. Confirming the existence of WIMPs would not only solve the dark matter mystery, but also potentially reveal new fundamental aspects of particle physics and the fabric of the universe. Scientists employ various sophisticated techniques to directly detect dark matter particles, leveraging both underground detectors and advanced astronomical observatories. Although dark matter does not interact with light and is therefore invisible to traditional telescopes, it is theorized to interact via gravity and potentially the weak nuclear force, which forms the basis for direct detection attempts. One primary method involves large underground detectors designed to identify elusive interactions between dark matter particles and atomic nuclei. These detectors are situated deep underground to shield them from cosmic rays and other background radiation that could obscure potential signals. The most common materials used in these detectors are noble gases like xenon or argon, which are kept in a liquid state at ultra-low temperatures. When a dark matter particle interacts with the nucleus of an atom within the detector, it can produce tiny flashes of light or minute amounts of heat. These interactions are remarkably infrequent, given the weakly interacting nature of dark matter candidates like WIMPs. However, ultra-sensitive photodetectors and thermal sensors capture these rare events. Experiments such as the Xenont in Italy and the Lux Zeppelin in the United States exemplify this approach, employing enormous tanks of liquid xenon monitored for potential interactions. Another technique focuses on indirect detection methods. Scientists look for the byproducts of dark matter interactions in space, such as the gamma rays, neutrinos, or electron-positron pairs that could be generated if dark matter particles were to annihilate each other or decay. Instruments like the Fermi Gamma Ray Space Telescope observe regions such as the centers of galaxies, where the density of dark matter is believed to be high, searching for unexpected excesses of these particles. Particle accelerators offer another avenue for potential dark matter detection. By smashing protons together at extremely high energies, as done at the Large Hadron Collider in Switzerland, physicists attempt to recreate conditions similar to those following the Big Bang. The goal is to produce dark matter particles that could then be inferred from missing energy and momentum in collision events. This indirect signature would suggest the creation of particles that do not interact like those in the Standard Model, potentially indicating dark matter. Hence, scientists are employing an array of cutting-edge technologies and methodologies, pushing the boundaries of detection capabilities. While direct evidence of dark matter remains elusive, these innovative and complementary approaches significantly narrow down the possibilities, bringing us closer to uncovering one of the universe's greatest mysteries. Ultra-high-energy cosmic rays are particles, primarily protons or heavier atomic nuclei, that travel through space at nearly the speed of light and possess energies far exceeding those of typical cosmic rays. These particles can have energies millions of times greater than those produced in man-made particle accelerators, making them some of the most energetic particles in the universe. The precise origins of ultra-high-energy cosmic rays remain one of the great mysteries in astrophysics. However, several potential sources are thought to be responsible for their extraordinary energies. One hypothesis involves active galactic nuclei, which are supermassive black holes at the centers of distant galaxies. These AGNs are surrounded by vast accretion disks of gas and dust, which, when falling into the black hole, can get accelerated to incredible speeds, thereby generating powerful jets capable of propelling particles to such extreme energies. Another possible source could be gamma-ray bursts, which are among the most energetic events observed in the universe. These bursts occur when massive stars collapse into black holes or when binary neutron stars collide. The intense explosion releases enormous amounts of energy in a very short time, potentially accelerating particles to ultra-high energies. Supernova remnants within our own galaxy are also considered potential contributors, particularly those involving very massive stars. The shockwaves generated by supernova explosions can accelerate particles to high energies through a process known as Fermi acceleration. While supernovae are well-established sources of lower-energy cosmic rays, it is possible that under the right conditions, they could also produce ultra-high-energy cosmic rays. Furthermore, interactions between cosmic rays and interstellar or intergalactic magnetic fields can also play a role in accelerating particles. These magnetic fields can bend and twist particle trajectories, amplifying their energies over vast distances through a process known as diffusive shock acceleration. Detection and study of ultra-high energy cosmic rays involve ground-based observatories like the Pierre Auger Observatory in Argentina and the Telescope Array Project in Utah. These observatories use extensive arrays of detectors spread over large areas to capture and analyze the secondary particle showers produced when ultra-high-energy cosmic rays collide with molecules in Earth's atmosphere. By studying the patterns, isotropies, and energy spectra of these cosmic ray impacts, scientists hope to unravel the origins and acceleration mechanisms of these extraordinarily energetic particles. As we continue to gather data, the secrets of ultra-high-energy cosmic rays slowly start to reveal themselves, potentially offering new insights into some of the most violent processes in the cosmos. Cosmic ray air showers occur when high-energy cosmic rays, primarily composed of protons or heavier nuclei, enter Earth's atmosphere and collide with atmospheric particles. This collision initiates a cascade of secondary particles that spread out in an extensive shower, which scientists can detect and study using ground-based observatories. When a primary cosmic ray, traveling nearly at the speed of light, strikes a molecule in the upper atmosphere, it initiates a high-energy collision, producing a variety of secondary particles. These first-generation particles typically include pions, kaons, and other hadrons. The process is highly energetic, with the initial impact often resulting in the creation of hundreds or even thousands of secondary particles. As these secondary particles travel further into the atmosphere, they collide with additional molecules, generating even more particles. The shower grows exponentially, creating a complex web of interactions. During this cascade, pions and kaons quickly decay into lighter particles like muons, electrons, neutrinos, and photons. The photon interactions can lead to pair production, where a photon converts into an electron and its antimatter counterpart, the positron. Similarly, electrons and positrons can emit photons through a process called Bremsstrahlung, feeding back into the cascade and producing more particles. This chain reaction results in a broad shower of secondary particles that spreads wider as it propagates through the atmosphere. The composition of the secondary particles changes as the shower progresses. At lower altitudes, the shower predominantly consists of photons, electrons, and muons, as many of the hadrons have decayed or lost energy through interactions. Muons, being relatively stable and less interactive, can penetrate deep into the atmosphere, sometimes even reaching the ground, where they can be detected by sensitive instruments. Water Cherenkov tanks detect the Cherenkov radiation emitted when muons and electrons move through the water faster than the speed of light in that medium, creating a distinctive blue glow. Scintillators detect charged particles through the light produced when particles pass through specific materials. By analyzing the pattern, timing, and intensity of the detected particles, scientists can reconstruct the properties of the original cosmic ray, including its energy, arrival direction, and potentially its source. This information helps in understanding cosmic ray origins and the fundamental processes that govern high-energy particle interactions in the universe. The Oh My God particle refers to an ultra-high-energy cosmic ray detected on the evening of October 15, 1991, by the Fly's Eye Cosmic Ray Detector in Utah. It astonished scientists because it possessed an energy of roughly 300 million electron volts, a level far beyond what had ever been observed before and millions of times greater than particles encountered in man-made particle accelerators. What made the oh my god particle particularly surprising was its sheer energy, which challenged our understanding of how the universe can accelerate particles to such extreme levels. To put this into perspective, the kinetic energy of this single proton was roughly equivalent to that of a baseball traveling at substantial speed, around 90 kilometers per hour. Such energy levels are extraordinarily difficult to achieve considering the known mechanisms of particle acceleration in astrophysical environments. The detection of the oh my god particle raised numerous questions about the potential sources of such high-energy cosmic rays. Conventional astrophysical objects such as supernova remnants or even active galactic nuclei typically cannot account for the extraordinary energies observed. Some scientists speculated that exotic and rare astrophysical events like colliding neutron stars, supermassive black hole jets, or even processes related to the early universe just after the Big Bang might be responsible. Additionally, the oh my god particle also posed a puzzle related to the Greisen-Zatsepin-Kuzmin limit, which is a theoretical upper bound on the energy of cosmic rays. According to this limit, cosmic rays with energies above roughly 5 million electron volts should interact with the cosmic microwave background radiation, losing energy over vast distances. Therefore, observations of such high-energy particles suggest that they either originate from relatively nearby extragalactic sources or that some unknown mechanism allows them to preserve their energy over greater distances than currently understood. Since the detection of the oh my god particle, several other ultra-high-energy cosmic rays have been observed, but the original discovery remains a landmark event in astroparticle physics. These detections continue to spur research and debate about the processes capable of producing such phenomenal energies, pushing the boundaries of our understanding of the most energetic phenomena in the universe. Cosmic rays pose significant challenges and risks for space travel and the health of astronauts. These high-energy particles, originating from the sun, distant stars, and other cosmic sources, can have profound effects on both the spacecraft and the human body. One of the primary concerns is the health risk arising from prolonged exposure to cosmic rays. Unlike Earth's surface, which benefits from the planet's magnetic field and atmosphere acting as protective shields, space lacks such defenses. Consequently, astronauts are directly exposed to these high-energy particles, which can penetrate human tissue and even spacecraft materials. The radiation can cause various biological effects, including damage to DNA and cellular structures, increasing the risk of cancer, cataracts, neurological disorders, and other health issues. The longer the mission, such as a journey to Mars, the greater the cumulative exposure and associated risks. Beyond individual health, cosmic rays can also impact spacecraft electronics through a phenomenon called single-event effects. When high-energy particles strike electronic components, they can induce errors, disrupt operations, or even permanently damage critical systems. Ensuring the reliability of spacecraft and its instruments in the face of such potential disruptions is a vital part of mission planning and engineering. To mitigate these risks, several strategies are employed. Spacecraft are designed with shielding materials to reduce the exposure of astronauts and sensitive electronics to cosmic rays. Although complete protection is impossible without impractically heavy shielding, materials like polyethylene and water offer some degree of attenuation. Additionally, spacecraft trajectories and mission durations are carefully planned to minimize exposure during periods of heightened solar activity, such as solar flares, which can significantly elevate the already considerable levels of radiation in space. For astronaut health, space agencies are also exploring the development of pharmaceuticals and other medical countermeasures that might help mitigate the effects of radiation exposure. Meanwhile, continuous monitoring of radiation levels using onboard sensors helps provide real-time data to assess and respond to elevated risks during the mission. In conclusion, cosmic rays present a formidable challenge for space exploration. Through advanced engineering, prudent mission planning, and ongoing research into protective measures, the goal is to safeguard astronauts as humanity pushes further into the cosmos. The broader understanding and mitigation of these effects are essential to the success and health of future long-duration space missions. Neutrino detectors, these remarkable instruments, allow scientists to peer into the very heart of some of the universe's most dramatic events. Unlike photons or charged particles, neutrinos barely interact with matter. This makes them incredibly challenging to detect, but simultaneously, perfect messengers from the extreme environments where they originate. For instance, they can travel directly from supernovae or the depths of the sun without being deflected or absorbed, carrying crucial information about those sources. By catching these elusive particles, neutrino detectors help us understand processes like nuclear fusion inside stars. The sun, powered by such fusion reactions, emits a constant stream of neutrinos. Studying them gives us direct evidence of the sun's inner workings, validating models of stellar physics. Similarly, detecting neutrinos from supernovae helps scientists investigate the explosive deaths of massive stars, shedding light on the production of heavy elements in the universe and the birth of neutron stars or black holes. Neutrinos even offer insights into the most fundamental aspects of physics. For instance, their ability to change from one type to another, a phenomenon known as neutrino oscillation, has provided compelling evidence that they indeed have mass, contrary to earlier assumptions. This discovery has profound implications for our understanding of particle physics and the fundamental forces governing the universe. Furthermore, exploring neutrinos from extragalactic sources opens up a new window into high-energy astrophysics. These particles might originate from active galactic nuclei or other mysterious cosmic phenomena, giving researchers clues about the most energetic processes in the cosmos. By studying neutrinos, scientists obtain a unique and otherwise unreachable perspective on both the most distant and the most hidden corners of the universe. Time dilation is a fascinating consequence of Einstein's theories of relativity and plays a crucial role in the functionality of global positioning system satellites. These satellites orbit the Earth at high speeds and at different altitudes compared to the planet's surface. According to general relativity, time runs slower in stronger gravitational fields, which means clocks on Earth's surface tick slightly slower than those further away in space. Meanwhile, special relativity predicts that due to their high velocities, time on board the satellites also runs slightly slower compared to a stationary observer on Earth. For the global positioning system to work accurately, the clocks on these satellites must synchronize precisely with clocks on Earth. Without adjusting for time dilation, even a tiny discrepancy can result in significant errors in position calculations. Specifically, the combined effects of special and general relativity mean that the satellite clocks tick faster than those on Earth by about 38 microseconds per day. While this might seem minuscule, over time it would lead to significant errors in position measurements, errors as large as 10 kilometers per day. To counteract this, the clocks on global positioning system satellites are preset to tick slightly slower before launch, ensuring that when they reach orbit, they match the pace of Earth's clocks. Additionally, onboard computers continuously adjust the satellite time to account for any relative motion and gravitational differences. Ensuring this level of precision is essential for the myriad applications that rely on the global positioning system, from navigation and mapping services to synchronizing telecommunications and even aiding in financial transactions. Time dilation adjustments thus embody the elegant interplay between theoretical physics and practical technology, underscoring how our understanding of the cosmos directly impacts everyday life. Gravitational waves are ripples in the fabric of space-time itself, caused by some of the most violent and energetic processes in the universe. Predicted by Albert Einstein's theory of general relativity, these waves travel at the speed of light and are generated when massive objects accelerate, especially in scenarios involving extreme gravitational fields. Examples include the merging of black holes or neutron stars, supernova explosions, and even the rapid rotation of massive stars. Detecting these elusive waves requires extremely sensitive instruments, as they cause space to stretch and compress by minuscule amounts. The most prominent tool for this task is the Laser Interferometer Gravitational Wave Observatory, known as LIGO. LIGO consists of two L-shaped interferometers, one in Washington State and the other in Louisiana, each with arms that are kilometers long. A laser beam is split and sent down each arm. If a gravitational wave passes through, it changes the length of the arms slightly, altering the time it takes for the laser beams to return and recombine. When the beams return and recombine, any difference in length will cause an interference pattern, which can be measured with astonishing sensitivity. In 2015, LIGO made the first direct detection of gravitational waves from a collision of two black holes, a discovery that confirmed a major prediction of general relativity and opened an entirely new way to observe the universe. This event marked the beginning of gravitational wave astronomy. With advancements in technology and additional detectors like the Virgo in Italy and the upcoming Kagra in Japan, our ability to pinpoint the sources of these cosmic waves is improving. By studying gravitational waves, scientists aim to uncover details about objects and events previously hidden from our view, giving us a deeper understanding of the dynamics of the cosmos. Wormholes, theoretical passages through space-time, have long captured the imagination with the enticing possibility of faster-than-light travel. Based on solutions to Einstein's equations of general relativity, wormholes could provide shortcuts between distant points in the universe. Imagine a tunnel with two ends located in different parts of space and time. If such a tunnel existed, traversing it could potentially allow one to travel great distances instantaneously, bypassing the limitations of light speed. However, the concept of using wormholes for faster-than-light travel faces several significant hurdles. The first challenge is stability. Most solutions for wormholes suggest they would collapse almost instantly upon formation, preventing anything, even light, from passing through. To keep a wormhole open and traversable, some form of exotic matter with negative energy density would be required. Such matter would counteract the natural tendency of the wormhole to pinch off, but creating or sustaining this exotic matter is beyond our current technological and scientific capability. Even if we could stabilize a wormhole, there are questions about their traversability and safety. The intense gravitational forces near the throat of a wormhole could potentially stretch and compress anything trying to pass through it, a process often referred to as spaghettification. Furthermore, solutions involving wormholes sometimes imply the existence of causality paradoxes, like the possibility of time travel, which introduces a host of theoretical and practical complications. While wormholes remain a fascinating idea in theoretical physics and a staple of science fiction, actual evidence for their existence or our ability to use them for travel remains elusive. As of now, they are rich arenas for thought experiments and underline the profound complexities of spacetime, but they are far from providing a practical solution for faster-than-light travel. Nonetheless, studying wormholes continues to push the boundaries of our understanding, challenging scientists to think beyond the limits of known physics. Frame dragging, also known as the lens-Thirring effect, is a fascinating phenomenon that occurs in the vicinity of rotating massive objects. According to Einstein's theory of general relativity, mass and energy can warp space-time, creating the gravitational effects we observe. However, when an object rotates, it does more than just warp space-time. It also drags it along with its rotation. Imagine space-time as a kind of viscous fluid and a rotating object, like a star or black hole as a stirrer. As the object spins, it twists the space-time around it. This effect is most pronounced near extremely massive and rapidly rotating bodies, such as neutron stars and black holes. The closer one gets to these objects, the stronger the frame-dragging effect becomes. Detecting frame dragging is incredibly challenging because its effects are subtle and require sensitive instrumentation. One of the most compelling confirmations of this phenomenon came from NASA's Gravity Probe B mission. Launched in 2004, the spacecraft carried ultra-precise gyroscopes intended to measure the tiny angle changes caused by the Earth's rotation dragging space-time around it. After years of data analysis, the results confirmed the presence of frame dragging, albeit at a very small scale. Frame dragging has significant implications for our understanding of the cosmos. Around rotating black holes, for instance, this effect could influence the paths of particles and light, shaping the structure and dynamics of accretion disks and jets emitted by these enigmatic objects. By studying frame dragging, scientists not only test and refine our understanding of general relativity, but also gather crucial insights into the complex behaviors near some of the most extreme environments in the universe. The twin paradox is a thought experiment that offers a vivid demonstration of time dilation, a concept rooted in Einstein's theory of special relativity. In this scenario, imagine two identical twins. One remains on Earth while the other embarks on a journey through space at a velocity close to the speed of light. According to special relativity, the twin traveling at high speed experiences time more slowly compared to the twin who stays behind. Here's how the paradox unfolds. The traveling twin sets off on a journey to a distant star at near light speed and then returns to Earth. Upon reuniting with the Earth-bound twin, the traveling twin finds less time has passed for them than for their sibling who remained on Earth. While the Earth-bound twin may have aged, say, 10 years, the traveling twin might have aged only a fraction of that time, depending on the exact speed and duration of the journey. This discrepancy arises because, as per special relativity, moving clocks run slower when observed from a stationary frame of reference. The term paradox emerges because it initially seems counterintuitive. One might wonder if each twin could consider the other as moving, so why wouldn't they both experience time dilation equally? The resolution lies in the fact that the traveling twin undergoes acceleration and deceleration during their journey, breaking the symmetry of the situation. This makes the traveling twin's frame of reference non-inertial, different from the stay-at-home twin's inertial frame. The twin paradox illustrates the real and measurable effects of relativity. Indeed, this effect is not just a theoretical curiosity. It has practical applications, such as in the functioning of the Global Positioning System satellites, where time dilation must be accounted for to maintain the accuracy of navigation signals. Thus, the twin paradox offers a compelling glimpse into the strange and counterintuitive nature of time in our relativistic universe. The mysterious gamma-ray glow at the center of our galaxy, often referred to as the galactic center GeV excess, has puzzled astronomers since its discovery. These high-energy gamma rays, detected by telescopes like the Fermi Gamma Ray Space Telescope, seem to emanate from an area densely packed with stars, dust, and energetic phenomena. The exact source of this gamma-ray emission is still under investigation, and several compelling theories have been proposed. One significant hypothesis suggests that dark matter particles might be annihilating each other in the dense region of the galactic center. Dark matter, which makes up a substantial portion of the universe's mass, remains largely undetectable except through its gravitational effects. If dark matter particles occasionally collide and annihilate, they could produce high-energy gamma rays as a byproduct. This would be a groundbreaking discovery, shedding light on the elusive nature of dark matter. Another theory attributes the gamma ray excess to a population of millisecond pulsars. These are rapidly rotating neutron stars that emit beams of radiation, including gamma rays. They are thought to be numerous in the crowded central regions of our galaxy. If these millisecond pulsars are indeed the source, it would mean that our understanding of the stellar population and high-energy processes in the inner galactic core needs significant adjustment. Whoa. Alternatively, the gamma-ray glow could result from interactions between cosmic rays and the dense gas clouds in the galactic center. Cosmic rays, which are high-energy particles traveling through space, can collide with gas atoms, producing gamma rays in the process. Given the complex environment of the galactic center, with its intense magnetic fields and high stellar activity, such interactions could plausibly generate the observed gamma-ray excess. As scientists continue to explore these possibilities, each potential explanation offers a fascinating glimpse into the dynamic and energetic processes at play in our galaxy's core. Understanding the true source of this gamma-ray glow not only unravels a cosmic mystery, but also enhances our knowledge of the fundamental forces and particles that shape the universe. Supermassive stars like R136A1, found in the dense star cluster R136 in the Large Magellanic Cloud, represent some of the most extreme cosmic phenomena. Forming such enormous stars, which can have masses hundreds of times that of our Sun, requires specific and exceptional conditions that are still a subject of intense study and debate among astronomers. The formation process begins within giant molecular clouds, vast regions of cold gas and dust where stars are born. For a supermassive star to form, a particularly dense region within one of these clouds must collapse under its own gravity. The key to generating a star as massive as R136A1 lies in the accumulation of an enormous amount of material from the surrounding cloud. This might happen in regions where star formation is particularly vigorous and the molecular cloud has unusually high mass and density. Once the progenitor gas cloud collapses, it forms a protostar that rapidly accretes more and more material. In environments like the R136 star cluster, neighboring stars and intense radiation can drive this accretion process, not only feeding the growing protostar, but also helping to clear away excess gas that might otherwise limit its growth. Despite these aiding factors, maintaining stability is a challenge because the massive star's intense radiation pressure can counteract gravity and hinder further growth. As these supermassive stars evolve, they burn through their nuclear fuel at an incredibly rapid rate. Their cores reach extreme temperatures and pressures, allowing for the fusion of heavier elements. However, this accelerated fusion process means that their lifespans are astonishingly brief, typically just a few million years compared to the billions of years for lower-mass stars like our Sun. Towards the end of their life cycle, supermassive stars undergo dramatic transformations. They might explode as supernovae or even hypernovae, releasing vast amounts of energy and enriching the interstellar medium with heavy elements. In some cases, they leave behind a dense core that collapses into a black hole. Through these cataclysmic ends, supermassive stars play a crucial role in the cosmic cycle of matter and the evolution of galaxies. Each stage of their life cycle offers invaluable insights into the extreme conditions and processes that shape the universe. High-velocity clouds are enigmatic, fast-moving clouds of gas that zip through the halo of the Milky Way, often at speeds hundreds of kilometers per second relative to the galaxy's rotation. Their origins are varied and complex, pointing to multiple potential sources and mechanisms that contribute to their formation. One leading hypothesis suggests that some of these high-velocity clouds are remnants of the galactic fountain process. In this scenario, supernova explosions within the Milky Way's disk propel gas outward into the halo. This gas then cools, condenses, and eventually falls back toward the galactic plane. During its return journey, this recycled material can appear as high-velocity clouds, essentially rejuvenating the galaxy with newly cooled gas that contributes to future star formation. Another plausible source for high-velocity clouds is the interaction between the Milky Way and its satellite galaxies. As smaller galaxies, like the Magellanic Clouds, orbit and occasionally pass through the Milky Way's halo, their gravitational interactions and tidal forces can strip gas from these satellites. This stripped gas can then manifest as high-velocity clouds. Observations suggest that the Magellanic Stream, a long tail of gas trailing from the Magellanic Clouds, may contribute significantly to these high-velocity phenomena. Furthermore, some high-velocity clouds could be primordial gas left over from the formation of the Milky Way itself. These clouds might consist of relatively unprocessed, pristine material, representing the remains of the gas reservoir from the early universe that settled into the galaxy's halo. Studying these clouds can offer invaluable clues about the conditions of the early universe and the processes of galaxy formation and evolution. Regardless of their origins, high-velocity clouds play a crucial role in our understanding of galactic dynamics and the ongoing processes that shape the Milky Way. By observing and analyzing these swift gas clouds, astronomers uncover layers of complexity in our galaxy's history, interactions, and the continuous cycle of matter within the galactic environment. When galaxies collide and merge, these awe-inspiring cosmic events unfold over millions to billions of years, transforming the structures and dynamics of the galaxies involved. The process begins as galaxies, under the influence of mutual gravitational attraction, draw closer to each other. Contrary to a typical notion of violent impacts, individual stars within galaxies rarely collide due to the vast distances separating them. Instead, the interactions primarily involve the gravitational forces exerted on the stars, gas, and dark matter within the galaxies. As galaxies approach each other, their gravitational fields create tidal forces that distort their shapes. Spiral arms may become elongated or twisted, and streams of stars and gas can be flung out into intergalactic space. During these close encounters, the gas within the galaxies can experience intense compression, leading to bursts of star formation. Astronomers call these episodes starbursts, which can produce new stars at rates much higher than usual. Eventually, the galaxies pass through each other, but gravity pulls them back together, causing them to engage in several additional encounters and passes. These interactions dissipate their relative kinetic energy, causing them to coalesce into a single larger galaxy. Over time, the merging process leads to the mixing and settling of the various components. The initially chaotic motions of stars smooth out, often transforming the progenitor's morphologies. For instance, the merger of two spiral galaxies typically results in an elliptical galaxy, characterized by random stellar orbits and a more spheroidal shape. Galactic mergers are fundamental processes in the hierarchical model of cosmic structure formation. They are instrumental in forming larger galaxies from smaller ones, a process known as hierarchical clustering. The evidence of past mergers is abundant in observations of galaxies with peculiar shapes, tidal tails, and stellar streams, the remnants of earlier galactic cannibalism. Even our own Milky Way is part of this cosmic dance, still in the process of absorbing smaller satellite galaxies like the Sagittarius dwarf galaxy. These mergers not only reshape galaxies but also influence the growth and activity of supermassive black holes at their centers. When galaxies merge, the inflow of gas can fuel these black holes, leading to active galactic nuclei that shine brightly as quasars or other luminous objects. Through these dramatic and transformative interactions, galaxy collisions and mergers play a critical role in the evolution and diversity of the cosmos. The mysterious ripples observed in the Milky Way's disk have intrigued astronomers, revealing much about the dynamic processes shaping our galaxy. These ripples, or oscillations, occur in the distribution and velocities of stars and gas within the galactic disk, hinting at past and ongoing perturbations. Multiple factors might be responsible for these undulating motions, with some of the leading explanations focusing on interactions with other galaxies and internal dynamical processes. One prominent hypothesis suggests that the ripples are the result of tidal interactions with nearby satellite galaxies, such as the Sagittarius dwarf spheroidal galaxy. As this smaller galaxy orbits and repeatedly passes through the Milky Way's disk, its gravitational influence could induce waves or ripples in the disk's structure. This scenario is akin to dropping a pebble into a pond, where the initial disturbance sets off concentric waves, though in the case of galaxies, the interactions are vast and occur over timescales spanning millions of years. Another contributing factor might be ancient collisions and mergers with smaller galaxies or dark matter clumps. Such events would have stirred up the stars and gas in the Milky Way, leaving behind enduring ripples long after the initial collision. These disturbances could persist as the galaxy gradually settles back into equilibrium, providing a historical record of past cosmic interactions. Additionally, the bar-shaped central region of the Milky Way, known as the galactic bar, might play a role in creating these ripples. The bar rotates and exerts gravitational forces on the rest of the galaxy, potentially inducing waves and spiral patterns in the disk. This internal dynamical effect can perpetuate and amplify existing ripples, contributing to the complex structure we observe. Studies utilizing data from the Gaia Space Observatory have provided invaluable insights into these ripples. Gaia's precise measurements of the positions, distances, and motions of stars across the Milky Way allow astronomers to map and model the disk's oscillations in unprecedented detail. By understanding the origins and behaviors of these ripples, scientists can gain deeper insights into the Milky Way's past interactions and internal dynamics, revealing the intricate and ongoing processes that shape our galaxy's evolution. The hypothesis of Planet 9, a potential large unseen planet in the far reaches of our solar system, has garnered significant interest among astronomers. The evidence suggesting its existence comes primarily from the peculiar orbits and behaviors of several distant Kuiper Belt objects and other trans-Neptunian objects. These objects follow highly elongated and tilted orbits, which are difficult to explain through the gravitational influence of known planets. Relatively recently, researchers have noted that the orbits of these distant objects exhibit unusual clustering. Rather than being randomly distributed, their perihelia, the points in their orbits closest to the Sun, seem to cluster together. This gravitational shepherding effect strongly hints at the presence of an unseen massive body, roughly estimated to be 10 times the mass of Earth. If Planet 9 exists, its gravitational influence would account for the observed alignment and clustering of these distant objects over long timescales. In addition to this clustering, Planet 9's gravitational pull might also explain other anomalies in the solar system. For instance, some orbits of the extreme trans-Neptunian objects show orbital inclinations that rise to high angles relative to the plane of the solar system. The tilted orbits of these objects are challenging to justify without invoking an additional gravitational perturber like Planet 9. Further indirect evidence comes from simulations and models. When researchers incorporate a hypothetical Planet 9 into their simulations of the solar system, the resulting orbital alignments and behaviors closely replicate the observed distributions of distant trans-Neptunian objects. These models strengthen the case for a large, distant planet's gravitational influence shaping the outer solar system. Though the evidence remains compelling, it is important to underscore that Planet 9 has not yet been directly observed. The vast distance, dimness, and slow movement make it extremely challenging to spot with current telescopes. Efforts are ongoing, with researchers utilizing next-generation telescopes and advanced surveys to scan the sky for this elusive object. If Planet 9 is eventually confirmed, it will redefine our understanding of the solar system's architecture and provide insights into its formation and evolution. The prevailing theory for the Moon's formation is the giant impact hypothesis, which suggests that the Moon resulted from a colossal collision between the early Earth and a Mars-sized protoplanet known as Theia. This cataclysmic event, occurring over 4 billion years ago, would have ejected a substantial amount of debris into orbit around the Earth. Over time, this debris coalesced due to gravitational forces, forming what we now recognize as the Moon. This theory elegantly explains the Moon's composition, which is strikingly similar to Earth's. Analyzing lunar samples brought back by Apollo missions, scientists discovered that the Moon consists primarily of silicates, much like Earth's crust and mantle. The oxygen isotopic composition of lunar rocks also closely matches that of Earth's. This indicates a common origin, suggesting that the material making up the Moon primarily came from the outer layers of Earth and Theia, which had already undergone significant differentiation. The aftermath of the impact would have led to a molten disk around Earth, composed of superheated silicate vapor and liquid. As this disk cooled and condensed, it formed the proto-Moon. The high temperatures during the collision and subsequent coalescence would have caused volatile elements to vaporize and escape, which is why the Moon is deficient in these elements compared to Earth. Further supporting this theory is the fact that the Moon's core is much smaller relative to its size than Earth's core. During the collision, while most of Theia's iron-rich core likely merged with Earth's core, the ejected material that formed the Moon would mainly consist of mantle and crustal material, explaining its iron-poor composition. The giant impact hypothesis not only clarifies the Moon's formation and composition, but also provides insights into the early solar system's dynamic and violent environment. Understanding this process helps scientists piece together the narrative of planetary formation and the unique history shared between Earth and its natural satellite. The hexagonal storm at Saturn's North Pole is one of the most intriguing and unique phenomena in the solar system. This massive six-sided jet stream, first discovered by the Voyager spacecraft in the early 1980s and later observed in greater detail by the Cassini spacecraft, spans roughly 30,000 kilometers across. Its geometric precision and stability have captivated scientists and prompted extensive study. The leading theory behind the formation of this hexagonal pattern involves fluid dynamics and atmospheric phenomena. Saturn, a gas giant, has an atmosphere composed of hydrogen and helium with some heavier elements. The hexagon is believed to result from differential rotation and the interaction of jet streams at Saturn's polar region. Essentially, the planet's atmosphere consists of clouds moving at different speeds and directions, creating complex patterns of flow. In laboratory simulations, scientists have replicated similar shapes by rotating fluids at different speeds. For instance, when fluid inside a cylindrical container is spun at varying rates, a polygonal pattern can emerge due to shear forces and resonant waves. Saturn's atmosphere behaves analogously, where the hexagonal shape results from the interaction of deep atmospheric jets and velocity differences that create standing wave patterns. Another factor contributing to the stability and shape of the hexagon is the presence of a powerful polar vortex, which anchors the hexagonal jet stream in place. This vortex acts as a central point around which the storm system rotates, maintaining the hexagonal structure over time. Unlike Earth's weather systems, which change relatively quickly, Saturn's storm systems can last for decades or even longer, thanks to the uniformity and lack of solid surface to disrupt atmospheric flows. Understanding the hexagonal storm on Saturn provides insights into planetary atmospheres and fluid dynamics under extreme conditions. It also helps scientists draw comparisons and find underlying principles that apply to atmospheric phenomena both within our solar system and on exoplanets, revealing the broad applicability of fluid dynamic theories in varied cosmic environments. Venus's retrograde rotation, meaning it spins in the opposite direction to most other planets in the solar system, is a puzzle that continues to captivate astronomers. Unlike Earth, Mars, and most other planets which rotate counterclockwise when viewed from above their north poles, Venus rotates clockwise. This means that on Venus, the Sun rises in the west and sets in the east. Several theories attempt to explain this unusual rotational behavior. One prevalent hypothesis involves a giant impact scenario during the early formation of the solar system. Just as Earth experienced a cataclysmic collision that led to the formation of the Moon, Venus might have undergone a series of massive impacts with large protoplanets or planetesimals. These collisions could have significantly altered its rotational angular momentum, potentially reversing its spin direction. Another theory posits that tidal forces from the Sun may have played a role in Venus's rotation. Venus's atmosphere is incredibly dense, and the thick sulfuric acid-laden clouds create considerable atmospheric friction. Over billions of years, combined gravitational interactions with the Sun could have slowed its rotation to a near standstill, allowing minor forces or remaining angular momentum to gradually reverse the spin direction. This process is similar to how the Moon's tidal interactions with Earth have slowed its rotation and synchronized it with its orbit. Additionally, complex dynamics within Venus's interior and interactions with its thick atmosphere might have contributed to this unusual rotation. Venus's slow rotation rate, taking about 243 Earth days to rotate once on its axis, means that its atmosphere circulates faster than the planet itself. This atmospheric superrotation might exert surface stresses significant enough to influence the planet's rotational direction over astronomical timescales. Understanding Venus's retrograde rotation not only sheds light on the history and evolution of our nearest planetary neighbor, but also enhances our general knowledge of planetary formation and dynamics. Comparing Venus with other celestial bodies helps to map out the diversity of planetary processes and scenarios that can unfold in our solar system and beyond. What creates the mysterious spokes in Saturn's rings? Well, these enigmatic features have baffled scientists for years. The spokes appear as radial, ghostly bands that move across Saturn's otherwise orderly and circular rings. The answer to their formation lies in the interplay of Saturn's magnetic field and tiny ice particles within the rings. Saturn's rings are composed mostly of ice and rock, with particles ranging from microscopic dust to chunks the size of boulders. The spokes are believed to be caused by the electrostatic charging of these smaller, dust-sized ice particles. When the particles encounter ultraviolet light from the Sun, or energetic particles in Saturn's magnetosphere, they can become electrically charged. As these particles gather a static charge, Saturn's powerful magnetic field can lift them slightly above the plane of the rings and cause them to align along the magnetic field lines. This creates the appearance of spokes that stretch across the rings and can travel at varying speeds. Essentially, it's as if the dust particles are being picked up and moved by invisible magnetic forces. The spokes are more visible when Saturn's rings are oriented edge-on to the Sun during the planet's equinoxes. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, provided valuable insights and images that have helped scientists understand this phenomenon better. While the complete picture is still not fully painted, the interplay between light, magnetic fields, and charged particles offers a fascinating glimpse into the complexity and dynamism of Saturn's rings. Gamma-ray bursts, often abbreviated as GRBs, are the universe's most powerful and luminous explosions, sending out intense flashes of gamma rays that can last from a few milliseconds to several minutes. These bursts release as much energy in a few seconds as the Sun does over its entire 10 billion-year lifetime. Gamma-ray bursts come primarily in two varieties: long-duration and short-duration bursts. Long-duration bursts, which last more than 2 seconds, are generally thought to be associated with the catastrophic collapse of massive stars in a supernova or hypernova event leading to the creation of a black hole or neutron star. The newly formed black hole or neutron star's intense gravitational forces cause the surrounding material to spiral inward at incredible speeds, generating staggering amounts of heat and pressure that result in the emission of gamma rays. Short-duration bursts lasting less than 2 seconds are often believed to result from the merger of two compact objects, such as neutron stars or a neutron star colliding with a black hole. These colossal collisions produce a violent gravitational disruption, creating bursts of gamma rays that are incredibly energetic as well. In both cases, the energy is channeled into narrow jets moving at nearly the speed of light. When one of these jets points directly at Earth, we observe it as a gamma ray burst. The intense energy behind these jets is a combination of the rapid rotation and intense magnetic fields involved in these cosmic disruptions, converting enormous amounts of gravitational energy into radiation. The study of gamma-ray bursts has been revolutionized by space telescopes and observatories like the Hubble Space Telescope and the Fermi Gamma-Ray Space Telescope. Their observations have revealed not only the mind-boggling power of these bursts, but also their role in shaping the universe, contributing to the creation of heavy elements and influencing the formation and evolution of galaxies. Kilonovae are stupendous cosmic events that occur when two neutron stars or a neutron star and a black hole spiral in towards each other and eventually merge. These cataclysmic collisions release tremendous amounts of energy and create conditions so extreme that they forge some of the heaviest elements in the universe, such as gold and platinum. To understand how kilonovae form, it's essential to grasp the nature of neutron stars. Neutron stars are incredibly dense remnants of massive stars that have undergone supernova explosions. When two neutron stars are gravitationally bound, they gradually lose energy through the emission of gravitational waves, causing them to spiral closer together until they ultimately collide. During the collision, the neutron-rich material is violently ejected into space. This material undergoes rapid neutron capture, a process known as the R process, which is responsible for creating heavy elements. In addition to producing a bright burst of gamma rays, the merger releases a glowing cloud of radioactive material that emits light as it decays. This glow is what we observe as a kilonova. Kilonovae are particularly significant for scientists studying the origin of heavy elements. Before the detection of a kilonova, it was hypothesized that supernovae were the primary sites of heavy element production. However, observations confirmed by events like the GW170817 merger in 2017 have demonstrated that neutron star mergers are an essential source of these elements. By studying the light from kilonovae, scientists can decipher the specific wavelengths emitted by various elements as they form. This allows them to build a more comprehensive picture of where and how the universe's heavy elements are synthesized. Such discoveries not only enrich our understanding of cosmic events, but also connect to the very materials that make up planets, and even ourselves. When neutron stars collide, the event is nothing short of spectacular and profoundly influential on our understanding of the cosmos. Neutron stars are the incredibly dense remnants of massive stars that have exploded in supernova. When two neutron stars are in a binary system, their immense gravity causes them to gradually spiral closer together over millions of years, losing energy through the emission of gravitational waves. As the neutron stars finally approach a critical distance, their gravitational interaction becomes titanic. The stars begin to deform and stretch, emitting increasingly intense gravitational waves, rippling through the fabric of space-time itself. This buildup culminates in a cataclysmic merger, releasing an immense burst of energy. The collision of neutron stars produces several phenomena in quick succession. First, a gamma-ray burst may occur, providing an intense burst of gamma rays detectable even from billions of light-years away. Simultaneously, the merger ejects an enormous amount of neutron-rich material into space. These rapidly moving ejecta undergo the R process, a rapid neutron capture process that synthesizes some of the heaviest elements such as gold, platinum, and uranium. Following the gamma-ray burst, the ejected material releases a glow as radioactive elements decay, creating what is known as a kilonova. This kilonova emission is visible across various wavelengths, including visible and infrared light. The sight of such an event confirms the role of neutron star collisions in producing heavy elements and enriches our understanding of nucleosynthesis. In the heart of the merger, the end state varies. The collision can result in the formation of a more massive neutron star or, if the mass is sufficient, collapse into a black hole. Observations of such events like the GW 170817 detected by LIGO and Virgo observatories have significantly advanced our knowledge of gravitational waves, the behavior of matter in extreme conditions, and the cosmic origin of heavy elements. White dwarf mergers are fascinating cosmic events that differ significantly from other types of stellar collisions. White dwarfs are the remnants of stars that were not massive enough to end their lives in a supernova. Instead, they have lost their outer layers and left behind a dense core composed mostly of carbon and oxygen. When two white dwarfs in a binary system spiral together and merge, the consequences are both unique and extraordinary. Unlike neutron star mergers, which often produce gamma-ray bursts and kilonovae, the merger of two white dwarfs can result in various outcomes depending on their combined mass. If their combined mass exceeds a critical threshold, around 1.4 times the mass of the Sun, the merger can trigger a type Ia supernova. This type of supernova is a powerful and luminous explosion that occurs when the merged white dwarf reaches the Chandrasekhar limit, igniting runaway nuclear fusion that obliterates the star completely. In cases where the combined mass does not reach this limit, the merging process can lead to the formation of a more massive and stable white dwarf. This newly formed white dwarf may have an atypical composition or slightly different spectroscopic properties compared to single white dwarfs. It can also significantly influence our understanding of stellar evolution and population dynamics within galaxies. The study of white dwarf mergers holds critical importance for several reasons. Type Ia supernovae are crucial cosmic distance markers, helping astronomers measure the expansion rate of the universe. Understanding how these events originate ensures greater accuracy in cosmological measurements. Moreover, white dwarf mergers can produce elements such as iron and nickel, contributing to the galactic chemical enrichment over billions of years. Thus, while neutron star collisions are often associated with gravitational waves, gamma-ray bursts, and the creation of heavy elements, white dwarf mergers provide valuable insight into the mechanics of stellar evolution, the origins of type Ia supernovae, and the broader dynamics of our universe. A magnetar explosion near our solar system would be cataclysmic and could have dramatic effects on Earth and the surrounding celestial bodies. Magnetars are a type of neutron star with extremely powerful magnetic fields, up to 1,000 times stronger than those of typical neutron stars. These immense magnetic fields can cause the star to undergo intense seismic activity, leading to outbursts or starquakes that release enormous amounts of energy in the form of gamma rays and X-rays. If a magnetar were to explode within a few light-years of our solar system, the immediate consequences would be profound. The burst of gamma rays and X-rays could potentially strip away the Earth's atmosphere. Without the protection of the atmosphere, life on the surface would be directly exposed to intense radiation, which could lead to mass extinctions. Additionally, the gamma rays could cause chemical reactions that produce harmful compounds, further depleting the ozone layer and making the planet even more susceptible to lethal ultraviolet light from the sun. Such an explosion would also affect electrical and electronic systems on Earth. The intense magnetic activity associated with a magnetar explosion could induce electric currents in the Earth's crust and in power grids, potentially causing widespread electrical outages and damaging satellites and other electronic infrastructure in space. Scientific interest in magnetars is partly because of their potential to explain some of the most energetic events in the universe. Observing the aftermath of such an explosion from a safe distance has enriched our understanding of magnetars and their influence on galactic environments. However, a close-by magnetar explosion remains a theoretical catastrophe, given that the nearest known magnetar is thousands of light-years away, allowing us to study these fascinating celestial objects without immediate threat to our solar system. While such an event is currently highly improbable, understanding magnetars and their behavior remains crucial for grasping the varied and extreme phenomena present in the universe. Organisms that thrive in some of Earth's harshest environments are known as extremophiles. These hardy creatures can endure extreme conditions that would be lethal to most life forms. Their habitats include acidic hot springs, deep ocean hydrothermal vents, Antarctic ice, and even radioactive waste. The adaptations of extremophiles offer fascinating insights into the resilience of life and significantly influence our search for extraterrestrial life. One of the key ways extremophiles survive is through biochemical and structural adaptations. For instance, thermophiles, which live in exceedingly high temperatures, such as those around hydrothermal vents, have proteins and enzymes that are highly stable and functional even in boiling water. Similarly, psychrophiles, which thrive in freezing conditions, possess antifreeze proteins that prevent ice crystal formation within their cells, ensuring flexibility and function at sub-zero temperatures. Other extremophiles, like acidophiles and alkalophiles, thrive in highly acidic or basic environments, respectively. These organisms have specialized cellular mechanisms that maintain their internal pH at viable levels, irrespective of the external conditions. Meanwhile, radiation-resistant extremophiles, such as Deinococcus radiodurans, can repair remarkably extensive DNA damage caused by high doses of radiation thanks to their efficient and robust DNA repair systems. The existence of extremophiles on Earth widens our understanding of what constitutes a habitable environment. If life can adapt to such extreme conditions here, it opens up the possibility that life could exist in similarly harsh environments on other planets or moons. For example, the icy moons of Jupiter and Saturn, like Europa and Enceladus, with their subsurface oceans heated by tidal forces, or Mars, with its potential subglacial habitats, are considered promising places to search for life. Studying extremophiles not only informs us about the limits of life on Earth, but also guides astrobiological missions in the search for life beyond our planet. The adaptability and resilience of these organisms inspire hope that life, in some form, might exist in the seemingly inhospitable reaches of our solar system and perhaps even beyond. The conditions inside gas giant planets like Jupiter are extreme and unlike anything we experience on Earth. Jupiter, the largest planet in our solar system, possesses an intricate and immensely dynamic internal structure. Starting from the outermost layers, Jupiter's atmosphere is composed primarily of hydrogen and helium, with traces of methane, ammonia, water vapor, and other molecules. The upper atmosphere is characterized by powerful storms, including the famous Great Red Spot, a colossal storm that has raged for centuries. Below the cloud tops, pressures and temperatures rise dramatically. As you descend further into Jupiter's atmosphere, the increasing pressure causes the hydrogen gas to transform into different states. At deeper levels, the temperature climbs to thousands of degrees Fahrenheit. Approximately 1,000 miles down, the pressure is so high that hydrogen turns into a dense and hot liquid. This region, known as the liquid metallic hydrogen layer, is crucial to Jupiter's unique properties. In this state, hydrogen behaves like an electrically conductive metal, contributing to the generation of Jupiter's powerful magnetic field through a dynamo effect. Beneath this liquefied layer, it is believed that Jupiter houses a core that might be composed of rock and metal. Although the exact nature of Jupiter's core is still a topic of research and debate, the core is thought to be surrounded by a thick envelope of liquid metallic hydrogen and helium. The intense pressures and extreme temperatures within Jupiter create an environment where materials behave in ways that are fundamentally different from conditions on Earth. For instance, the liquid metallic hydrogen layer generates planetary magnetic fields that are thousands of times stronger than Earth's, which influences Jupiter's magnetosphere and contributes to its impressive auroras. Understanding the conditions inside Jupiter not only enhances our knowledge of gas giants, but also provides critical insights into the formation and evolution of our solar system. Missions like the Galileo orbiter and the Juno spacecraft have been instrumental in gathering data about Jupiter's atmosphere, magnetic field, and interior, deepening our understanding of these massive and mysterious worlds. Stars that exist in the extreme environment near supermassive black holes endure a precarious existence, subject to intense gravitational forces and high-energy radiation. Supermassive black holes, often found at the centers of galaxies, exert enormous gravitational pull, creating a region of space with conditions that are profoundly hostile to most stars. The survival of stars in such environments is a testament to the dynamic dance of celestial mechanics and astrophysical processes. One of the key factors in a star's survival near a supermassive black hole is its orbit. Stars that maintain stable elliptical orbits can avoid straying too close to the black hole's event horizon, the region beyond which nothing, not even light, can escape. These stable orbits are often the result of gravitational interactions with other stars or massive objects, which help shepherd the star along a safe trajectory. Stars that do wander too close can be torn apart by tidal forces in a process known as tidal disruption. Another factor is the mass of the supermassive black hole and the star itself. The gravitational influence of a supermassive black hole extends far, but near the event horizon, the tidal forces become extreme. Stars composed of denser material or those with strong self-gravity can resist being torn apart to a greater extent than less dense stars. However, even these stars are at risk if they come too close. High-energy radiation and intense gravitational forces can strip stellar material over time. Despite these conditions, some stars manage to coexist in these hostile environments. In the regions near supermassive black holes known as accretion disks, stars can interact with dense gas and other stellar material. Occasionally, stars can even form from the dense gas and dust within these disks, though such stars might have shorter lifespans due to the hostile environment. Additionally, studies of stars near the supermassive black hole at the center of our Milky Way, referred to as Sagittarius A star, have revealed stars that are on tight, rapid orbits. Observations of these stars provide critical insights into the behavior of matter and gravity in extreme environments. The survival and dynamics of stars near supermassive black holes offer scientists valuable opportunities to test theories of general relativity and to understand the complex interactions that govern galactic centers. Therefore, while the environment near supermassive black holes is indeed extreme, the survival of stars in this region illustrates the delicate balance of gravitational forces, orbital dynamics, and the resilient nature of stellar objects. Understanding these interactions enhances our comprehension of astrophysical processes in some of the universe's most formidable locales. Matter, under the extreme gravity of a neutron star, experiences conditions that are remarkably intense and beyond anything found on Earth. Neutron stars, which are the remnants of massive stars that have exploded in supernova, pack more mass than the Sun into an incredibly small volume, roughly the size of a city. The gravitational force near the surface of a neutron star is overwhelmingly strong. To put it in perspective, gravity on a neutron star is about 10 billion times stronger than on Earth. This intense gravity has profound effects on matter in several ways. Firstly, the atoms in matter are crushed to extraordinary densities. Electrons are pushed into protons, resulting in a sphere composed mainly of neutrons. This process leads to an incredibly dense core, where a sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. The extreme pressures prevent the matter from collapsing further, stopping just short of creating a black hole. Inside a neutron star, the structure is layered. The outer crust consists of a lattice of atomic nuclei bathed in a sea of electrons. As you go deeper, the density increases and protons and electrons merge into neutrons. Beyond this point lies the inner crust, where the properties of matter become even stranger, potentially forming exotic states such as superfluid neutrons or superconducting protons. The core of a neutron star remains one of the most mysterious and debated areas in astrophysics. It's hypothesized that matter here might undergo further transformations, possibly forming a soup of quarks and gluons, or even more exotic particles like hyperons or boson condensates. However, the exact nature of this core remains an area of active research, as it involves conditions that are currently beyond our ability to replicate in laboratories. The extreme gravity of a neutron star also leads to remarkable astrophysical phenomena. These stars often have strong magnetic fields and can emit powerful beams of radiation, detectable as pulsars if these beams sweep across the Earth. Studying neutron stars and their gravitational effects provides vital clues about nuclear physics, the behavior of matter at ultra-high densities, and the fundamental properties of gravity itself. Thus, matter in the proximity of a neutron star experiences crushing pressures and intense gravitational forces that transform it into states that push the boundaries of our understanding of physics. Exploring these conditions enables scientists to probe some of the universe's most extreme environments. Extremophiles, which are organisms that thrive in some of Earth's most inhospitable environments, have revolutionized our understanding of where and how life can exist. These remarkable creatures live in places once thought to be utterly lifeless, such as boiling hydrothermal vents on the ocean floor, acidic hot springs, and the sub-zero lakes buried beneath Antarctic ice. Their resilience informs scientists about the potential for life on planets and moons with seemingly extreme conditions. For example, the discovery of bacteria surviving and even flourishing in the intense radiation and cold of space-like conditions in Earth's deserts or deep within the crust gives researchers clues about what to look for if we were to search for life on Mars' harsh surface or beneath its icy caps. Similarly, the ability of certain microbes to metabolize sulfur and other chemicals in Earth's hot springs inspires curiosity about similar biochemical processes on moons like Jupiter's Europa or Saturn's Enceladus, where subsurface oceans might harbor similar environments. Astrobiologists study extremophiles to understand the biochemical adaptations that allow these organisms to endure high levels of radiation, extreme pressures, or complete darkness. They examine specific proteins, enzymes, and other molecular mechanisms that protect and repair cellular components. This scientific detective work helps us refine the instruments we send on space missions, tailoring them to detect subtle signs of life in hostile extraterrestrial environments. By mapping the extremophiles' varied preferences and resilience, scientists can identify potential habitats on other celestial bodies. Their findings suggest that life, if it exists beyond Earth, may not need the temperate, stable conditions we enjoy on our planet, but could instead be thriving in places we've only begun to imagine. This insight significantly broadens the scope of our search for extraterrestrial life, pushing humanity to reconsider where we might find our cosmic neighbors. Coronal mass ejections, known as CMEs, are massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. These colossal events are driven by the Sun's magnetic field. The Sun's atmosphere, despite its serene appearance, is a highly dynamic and chaotic environment. Twisted magnetic field lines, which get tangled and stressed over time, can suddenly snap and reconfigure. This process, known as magnetic reconnection, releases an enormous amount of energy, propelling solar material outward at astonishing speeds. When a CME is directed towards Earth, it can have profound effects. As the charged particles and magnetic fields from the CME collide with Earth's own magnetic field, they can generate geomagnetic storms. These storms can disrupt satellite communications, interfere with radio transmissions, and even impact navigation systems. Moreover, the induced electrical currents created by such disturbances can overload power grids, sometimes leading to widespread power outages. One of the most captivating effects of CMEs is the enhancement of the auroras, known as the northern and southern lights. These natural light displays are typically confined to polar regions, where Earth's magnetic field guides solar particles toward the poles. During a CME, these dazzling lights can become much more intense and even visible at much lower latitudes than usual, offering a spectacular visual reminder of our planet's dynamic relationship with the Sun. Satellites and space stations also face heightened risks from increased radiation during CMEs. This influx of energetic particles can damage sensitive electronics and pose health risks to astronauts. To mitigate these hazards, space agencies continuously monitor solar activity, providing early warnings when a CME is detected heading towards Earth. Through preparedness and advanced technology, we can better safeguard our technological infrastructure and space explorers from these powerful solar events. Solar flares, akin to massive explosions on the sun's surface, release tremendous amounts of energy, including radiation and energetic particles. When a solar flare heads towards Earth, its radiation and particles interact with our planet's magnetic field and atmosphere. This interaction can cause significant disruptions, particularly affecting the technology and communication systems we rely on daily. Radiation from solar flares can disturb the ionosphere, a critical layer in the Earth's atmosphere that can reflect and alter radio waves used for communication. High-frequency radio signals, essential for aviation, maritime communication, and emergency services, may experience blackouts. These interruptions can lead to the loss of vital data transmission, causing confusion and delays in critical operations. Furthermore, solar flares can compromise satellites orbiting the Earth. The increased radiation can damage or degrade sensitive satellite electronics and solar panels, leading to a potential loss of services like GPS navigation and satellite communication. This means that activities ranging from airline navigation to personal navigation devices and even financial transactions dependent on precise timing can be adversely affected. Not limited to communication systems, solar flares also pose threats to the power grid infrastructure. Energetic particles from the flare generate geomagnetically induced currents in the Earth's crust, which can overwhelm and damage transformers and other components of the electrical grid. This surge can result in widespread power outages and, in severe cases, can take considerable time and resources to repair, disrupting daily life and economic activities. Our growing dependency on sophisticated technology and interconnected communication systems makes us increasingly vulnerable to the effects of solar flares. As we venture further into space and expand our technological reach, understanding and mitigating the impacts of solar flare activity becomes ever more crucial. This is why continuous solar monitoring and developing robust protective measures for our technological infrastructure remain key priorities for scientists and engineers. The coronal heating problem is one of the long-standing mysteries in solar physics. It describes the perplexing phenomenon where the sun's outer atmosphere, known as the corona, is inexplicably hotter than its visible surface, the photosphere. While the photosphere is about 6,000 degrees Celsius, the corona burns at a staggering 1 to 3 million degrees Celsius, presenting a challenging enigma for scientists. The primary suspects behind this extraordinary heating are magnetic field interactions. The sun's magnetic field is far from static. It twists, tangles, and reconfigures constantly due to the turbulent motions deep within the solar interior. One hypothesis, known as magnetic reconnection, suggests that when these tangled magnetic field lines snap and reconnect, they release immense amounts of energy, heating the surrounding coronal plasma. Another intriguing theory involves a type of wave called Alfvén waves, named after the Swedish physicist Hannes Alfvén. These waves travel along magnetic field lines and may carry energy from the turbulent layers below the photosphere up into the corona. When these waves dissipate their energy, they could provide the necessary heat to explain the corona's high temperatures. Observations from spacecraft like NASA's Solar Dynamics Observatory and the Parker Solar Probe are crucial for studying these waves and their potential role in coronal heating. Despite significant progress, the precise mechanisms behind the coronal heating problem are still actively researched. Scientists employ a combination of observational data from space missions, theoretical models, and computer simulations to unravel this complex phenomenon. Understanding the coronal heating problem is not only fundamental for solar physics, but also for broader astrophysical contexts, as it can offer insights into the behavior of stellar atmospheres throughout the cosmos. Cosmic rays from solar events, particularly during solar storms and flares, can significantly impact air travel. These high-energy particles, which originate from the Sun, the distant galaxy, and beyond, can permeate the Earth's atmosphere. When solar activity intensifies, such as during solar flares or coronal mass ejections, the influx of these cosmic rays increases, leading to several potential challenges for aviation. At high altitudes, where commercial planes typically cruise, the atmosphere is thinner, providing less protection from these cosmic rays compared to sea level. Consequently, aircrew and passengers on high latitude or polar routes, where cosmic ray exposure is naturally higher, are particularly vulnerable during solar events. Increased exposure to cosmic rays can lead to higher doses of radiation, potentially affecting the health of frequent flyers and flight crew over time. Regulatory bodies keep track of these radiation levels, and airlines sometimes adjust flight paths or altitudes to minimize exposure during significant solar events. Cosmic rays can also interfere with avionics, the electronic systems vital for aircraft control and navigation. High-energy particles can cause transient errors known as single-event upsets in these sensitive electronic components. While modern aircraft are designed to be robust, these interferences highlight the necessity for thorough testing and resilience in avionics systems. Moreover, increased radiation in the atmosphere can disturb high-frequency radio communications, which are critical for air traffic control, especially over oceanic and remote areas where there is no radar coverage. During intense solar events, alternative communication methods, such as satellite communication, might be needed, although they too can face challenges. To mitigate these risks, space weather monitoring stations continuously observe solar activity. Real-time data and predictive models allow for timely alerts to the aviation industry, enabling airlines to take proactive measures to ensure the safety and reliability of air travel. This underscores the intricate connection between space phenomena and terrestrial technology, emphasizing the need for vigilance and adaptation in our increasingly interconnected world. The Sun's magnetic field reversal, known as the solar cycle, is a fascinating process driven by the complex dynamics within the Sun's interior. Roughly every 11 years, the Sun undergoes a complete magnetic flip where its north and south magnetic poles switch places. This magnetic reversal is a crucial aspect of solar activity, influencing phenomena like sunspots, solar flares, and coronal mass ejections that affect our solar system. At the heart of this magnetic flip is the Sun's dynamo mechanism, which operates deep inside the Sun's convective zone. This zone lies just below the Sun's surface and is characterized by turbulent convective motions where hot plasma rises, cools, and then sinks back down. These motions, combined with the Sun's rotation, generate the magnetic field through a process called the alpha-omega dynamo. In this mechanism, the differential rotation of the Sun, whereby the equator rotates faster than the poles, twists and stretches magnetic field lines in a process known as the omega effect. This creates the large-scale magnetic structures observed on the Sun's surface. Concurrently, the turbulent convective motions twist and shear the magnetic field lines in what is termed the alpha effect. Together, these effects create a feedback loop that periodically amplifies and then flips the magnetic field. As the solar cycle progresses, sunspots, temporary phenomena on the Sun's photosphere linked to the magnetic field, appear in greater numbers and gradually migrate toward the equator. During the peak of the solar cycle, called the solar maximum, the magnetic field is at its most dynamic, and the poles eventually swap. The cycle then begins to wind down towards a solar minimum, where solar activity diminishes and the magnetic field resets in preparation for the next reversal. This intricate ballet of magnetic forces within the Sun keeps scientists deeply engaged in understanding the exact mechanisms and predicting future solar activity. The implications of the solar cycle extend far beyond scientific curiosity, affecting space weather, satellite operations, and even Earth's climate, underscoring the importance of continued study and monitoring of our closest star. Molecular clouds, often termed stellar nurseries, are dense regions of gas and dust where new stars are born. These vast, cold clouds, composed largely of molecular hydrogen, are scattered throughout galaxies and represent the raw material for star formation. The process of star birth within these clouds is a captivating sequence of events driven by the forces of gravity and thermodynamics. The journey begins when a portion of the molecular cloud becomes unstable, often due to disturbances such as supernova shockwaves, nearby stellar winds, or interactions with other clouds. These perturbations compress the gas and dust, causing regions within the cloud to amass greater density. Once these regions, called clumps, reach a critical density, their gravitational pull overcomes the internal pressure, leading to further collapse. As the clump collapses under gravity, it begins to fragment into smaller, denser cores, which continue to collapse independently. This process increases the core's pressure and temperature. Eventually, the core's center becomes so hot and dense that nuclear fusion ignites, converting hydrogen into helium and releasing an immense amount of energy. This marks the birth of a new star, now known as a protostar. During this phase, the protostar continues to accumulate material from the surrounding gas and dust, forming a rotating disk known as an accretion disk. This disk is a bustling environment where planets and other celestial bodies might eventually form. The star remains enshrouded by the leftover material for a time, gradually stabilizing and clearing its surroundings through radiative pressure and stellar winds. Once the nascent star stabilizes and nuclear fusion balances the forces at its core, it becomes a main sequence star, shining brightly and entering the prolonged phase of stellar life. The story of star formation in molecular clouds is a testament to the dynamic and ever-changing nature of our universe. Observing these processes in action through telescopes and space missions allows scientists to uncover the mysteries of stellar evolution, shedding light on our own sun's origins and the broader tapestry of stars scattered across the cosmos. The eerie glow of planetary nebulae is a captivating and colorful spectacle that marks the final spectacular phase of medium-sized stars' lives, similar to our Sun. Far from being planets, planetary nebulae are actually vast shells of glowing gas and dust expelled from stars in their dying throes. As a star like our Sun nears the end of its life, it exhausts the nuclear fuel in its core. This fuel depletion causes the core to shrink and heat up while the outer layers expand and cool, transforming the star into a red giant. Over time, the increasingly unstable outer layers of the giant star are ejected into space by strong stellar winds, leaving behind a hot, dense core called a white dwarf. The white dwarf, although tiny in comparison to its former self, emits intense ultraviolet radiation. This radiation energizes the expelled gas, causing it to glow brightly. This process, known as photoionization, is what gives planetary nebulae their distinctive luminescence. Hydrogen, the most abundant element, often emits a red or pink glow, while ionized oxygen produces brilliant hues of green and blue. The intricate shapes and vibrant colors of planetary nebulae are not just visual treats, but also reveal the complex interactions between the outgoing stellar material and the star's magnetic field, rotation, and any potential companion stars. The diverse morphologies, ranging from spherical to bipolar and even more intricate shapes, provide astronomers with clues about stellar dynamics and the processes governing the ejection of stellar material. Characterizing the structure and composition of planetary nebulae helps scientists understand stellar evolution and the chemical enrichment of the interstellar medium. These glowing celestial sculptures ultimately disperse their constituent elements back into space, contributing to the formation of new stars and planets, including the raw materials for potentially habitable environments. The light of planetary nebulae thus serves as a beautiful and poignant reminder of the cyclical nature of the cosmos. Supernova remnants, the majestic final episodes of a star's life, evolve through several fascinating stages, each unveiling more about the cosmos around them. These remnants are the debris left behind after a supernova explosion, when a massive star ends its life in a brilliant burst of energy. The remnants' evolution involves dynamic and complex interactions with the surrounding interstellar medium. The journey begins with the initial explosion, where the star releases an immense amount of energy, launching its outer layers into space at speeds of millions of kilometers per hour. This violent event creates a shockwave that races outward, compressing and heating the surrounding interstellar gas. Initially, the remnant is very energetic and bright, dominated by the blast wave, which can be observed as an expanding shell of hot, ionized gas. As the remnant expands, it enters the free expansion phase, where the ejected material moves relatively unimpeded by the interstellar medium. This phase can last for hundreds of years. During this time, the expanding shockwave continues to plow through space, sweeping up material and forming a thin, high-energy shell. The remnant glows in various wavelengths, including X-ray, visible, and radio, due to the heated gas and accelerated particles. Eventually, the remnant begins to collect more mass from the interstellar medium relative to its own ejected mass. This transition marks the onset of the Sedov-Taylor phase, which can last thousands of years. Here, the expansion slows down, and the remnant's shockwave becomes less driven by the initial explosion and more influenced by the external medium. Complex interactions between the shockwave and the interstellar medium create rich filamentary structures and turbulence within the remnant. In the final stage, known as the radiative or snowplow phase, the remnant cools and slows significantly, becoming less luminous. Radiative losses, where the remnant loses energy through radiation, dominate this phase, causing it to slow further and merge gradually with the interstellar medium. Over time, the supernova remnant disperses its enriched material, including heavy elements like iron and silicon, into the surrounding cosmos. This material contributes to future generations of stars, planets, and potentially life itself. The evolution of supernova remnants provides vital clues about the life cycles of stars, the dynamics of the interstellar medium, and the enrichment of galaxies with heavy elements. Observations from telescopes across various wavelengths continue to uncover the intricate details of these celestial phenomena, showcasing the immense forces and processes at play in our universe. The interstellar medium is the vast, often mysterious expanse of gas, dust, and cosmic rays that fills the space between stars within a galaxy. Though seemingly empty, this medium is incredibly rich and plays a crucial role in the life cycle of stars and the evolution of galaxies. The ISM is composed of multiple components, each with distinct properties and contributions to the cosmic environment. At its most basic, the ISM consists primarily of hydrogen and helium, with traces of heavier elements or metals, as astronomers refer to them. These heavier elements are the remnants of past stellar processes, such as supernova explosions and stellar winds. The gas component of the ISM exists in various physical states, ranging from cold, dense molecular gas to hot, diffuse ionized gas. Temperature, density, and ionization state can vary dramatically, leading to different phases within the ISM. One of the key constituents of the ISM is molecular clouds, which are dense and cold regions often considered the stellar nurseries where new stars form. These clouds, primarily composed of molecular hydrogen, can be thousands of times more massive than the Sun and serve as the raw material for star formation. Conversely, hot ionized gas exists at much higher temperatures, often reaching millions of degrees Kelvin, and fills the lower density regions known as the intercloud medium. Supernova remnants and massive stars contribute to this hot, ionized gas through their energetic outputs. Another notable component is interstellar dust, which consists of tiny solid particles made of elements like carbon, silicon, and iron. Despite making up only about 1% of the ISM by mass, this dust plays an essential role in astrophysical processes. It absorbs and scatters light, creating the dark patches and stunning color variations observed in nebulae. Dust facilitates the formation of molecules, such as hydrogen molecules on its surfaces, and serves as the bricks for building planets when star systems form. Interactions within and between these various components of the ISM result in a dynamic and evolving medium. Shock waves from supernovae, stellar winds, and other energetic processes continually shape and mold the ISM, creating complex structures and fostering the cycles of star formation and destruction. By studying the ISM, astronomers gain insight into everything from the birth of stars and planets to the large-scale structure and evolution of galaxies, emphasizing the ISM's integral role in the cosmic landscape. Bow shocks form when stars, particularly those moving at high speeds through the interstellar medium, create a region where their stellar winds interact with the surrounding gas and dust. Much like the bow wave produced by a ship moving through water, a bow shock is the result of the stellar wind, streams of charged particles emitted from the star, colliding with the interstellar medium. This collision compresses and heats the gas in a distinctive curved shock front. A star capable of producing a bow shock typically generates a powerful stellar wind. When this star moves through space, it pushes against the interstellar medium, creating a shock wave in front of it. The shape of the resulting bow shock depends on the relative speeds of the star and the stellar wind. If the stellar wind is strong enough to push back against the interstellar medium, the bow shock forms a curved, bow-like structure around the star. The boundary where the stellar wind slows down abruptly due to this interaction is called the termination shock, while the outermost edge, where the shock front meets the undisturbed interstellar medium, is known as the bow shock itself. Inside this boundary, between the termination shock and the bow shock, lies the astrosheath, a region filled with turbulent, compressed gas. Several fascinating cases of bow shocks have been observed, often around massive luminous stars like O-type and B-type stars, or even around older pulsars moving at high speeds. These observations are typically made in infrared wavelengths, where the heated dust and gas emit strongly. The shapes and sizes of these bow shocks can give astronomers clues about the star's velocity, the strength of its stellar wind, and the characteristics of the surrounding interstellar medium. By studying bow shocks, scientists can learn more about the dynamics of stellar motion and interactions within the interstellar medium. These structures reveal crucial information about a star's life and its environment, demonstrating the continuous and intricate dance between stars and the cosmic material through which they travel. Gravitational lenses provide a remarkable window into the universe, allowing us to observe distant galaxies that would otherwise be nearly impossible to see. This phenomenon leverages the concept of gravity's ability to bend light, a prediction famously confirmed by Einstein's theory of general relativity. Essentially, when a massive object, such as a galaxy or a cluster of galaxies, lies between a distant source and our observational point on Earth, its gravitational field acts like a lens, warping and magnifying the light from the distant source. Imagine light as a stream traveling through space. When it passes near a massive object, the gravitational pull of that object bends the light paths inward, much like how a glass lens bends light. This bending can magnify the light, brighten the image, and even split it into multiple images. The intervening object creating this effect is called a gravitational lens, while the distorted, magnified distant galaxy is referred to as the lensed source. Gravitational lenses come in various forms, from strong lenses creating pronounced arcs and multiple images to subtle weak lenses that slightly warp the appearance of the background galaxies. In spectacular cases, strong gravitational lenses can produce phenomena like Einstein rings, where the lensed source appears as a complete ring of light encircling the lensing object. The enhanced visibility provided by gravitational lensing allows astronomers to study galaxies and other cosmic structures that lie far beyond the reach of our most powerful telescopes. These distant galaxies, often from a very early period in the universe's history, reveal important details about the universe's formation and evolution. For instance, researchers can study the properties of primordial galaxies, the distribution of dark matter, and the large-scale structure of the cosmos. Additionally, gravitational lensing offers a unique method to study dark matter, which does not emit or absorb light, but has a significant gravitational influence. By analyzing the distortions caused by gravitational lenses, scientists can map the distribution of dark matter within lensing galaxies or clusters. Gravitational lenses exemplify the profound interconnectedness of the cosmos, enabling us to peer back in time and unravel the mysteries of the universe, blending the elegance of general relativity with the pursuit of understanding the distant reaches of space and time. The James Webb Space Telescope stands as a transformative tool for observing the early universe, boasting several innovative features that make it exceptionally powerful. Its primary asset is its unprecedented ability to observe infrared light, allowing it to peer through cosmic dust clouds and glimpse the faint ancient light from the first galaxies and stars that formed after the Big Bang. The JWST's mirrors and instruments are specifically designed to capture infrared wavelengths. As the universe expands, light from the earliest stars and galaxies shifts from the visible spectrum into the infrared due to the redshift effect. The JWST's primary mirror, which is over 6 times larger in area than the Hubble Space Telescopes, is optimized to capture this faint infrared light. Made up of 18 hexagonal segments coated in gold to enhance reflectivity, the mirror allows the telescope to gather more light, thus seeing further into the past. Another game-changing feature of the JWST is its location and cooling system. It operates in a stable orbit around the second Lagrange point, approximately 1.5 million kilometers from Earth. This positioning not only provides a stable environment free from Earth's atmospheric interference, but also allows the telescope to stay in constant communication with ground control. Moreover, operating in the cold of space, shielded by a sophisticated multi-layer sunshield, helps keep the instruments at extremely low temperatures. This cooling is critical for detecting the weak heat signals from distant objects, ensuring minimal infrared interference from the telescope itself. Equipped with 4 cutting-edge scientific instruments, the JWST can perform a wide range of astronomical observations. These instruments, comprising cameras, spectrographs, and coronagraphs, enable detailed imaging, spectroscopy, and the study of celestial objects' physical properties. With JWST, scientists can study not only the early universe but also star and planet formation, exoplanet atmospheres, and the chemical compositions of distant galaxies. The synergy of these advanced technologies propels the JWST far beyond previous telescopic capabilities. By observing the early universe with unprecedented clarity and depth, the JWST aims to answer fundamental questions about cosmic origins, the evolution of galaxies, and the mysteries of dark matter, offering a compelling glimpse into the most ancient epochs of the cosmos. Very long baseline interferometry, or VLBI, is an extraordinary technique that leverages the combined power of multiple radio telescopes spread across vast distances to achieve incredibly high-resolution observations. By synchronizing these widely separated telescopes, VLBI effectively creates a single, enormous virtual telescope with a baseline as large as the distance between the farthest participating telescopes. This ingenuity allows astronomers to observe fine details in cosmic objects, unattainable by individual radio telescopes. Here's how it works. Each radio telescope in the VLBI network collects radio waves emitted by celestial sources, such as distant galaxies, quasars, or supernova remnants. These radio signals are incredibly weak and travel vast distances, arriving at each telescope slightly out of sync due to the finite speed of light and the separation between the telescopes. To precisely capture this data, each telescope is equipped with highly accurate atomic clocks, often hydrogen masers, enabling it to timestamp the received signals down to nanoseconds. Captured data from each telescope is recorded and then sent to a central processing facility, known as a correlator. The correlator's job is to meticulously align these signals by accounting for the time differences based on the telescope's locations and their precise movements. By combining the data, the correlator constructs interference patterns that astronomers use to generate high-resolution images. This process enhances the ability to pinpoint and study celestial objects with a level of detail comparable to having a single telescope the size of the maximum distance between the individual radio telescopes. VLBI's power lies in its ability to achieve exceptional angular resolution, allowing scientists to observe and measure phenomena in remarkable detail. This technique has been instrumental in numerous groundbreaking discoveries, such as imaging the event horizon of a black hole for the first time with the Event Horizon Telescope, a global VLBI network. It also aids in studying the dynamics of quasars, mapping the distribution of matter in galaxies, and understanding pulsars and other compact objects. By overcoming the physical limitations of individual radio telescopes, VLBI exemplifies human ingenuity in astronomical observation, providing unparalleled insights into the universe's most distant and enigmatic objects. This collaborative effort across continents and, in some cases, including space-based antennas, showcases the power of synchronizing technology and precision for unlocking cosmic secrets. Neutrino detectors offer a unique and profound insight into the interior processes of the Sun, specifically its core where nuclear fusion occurs. Neutrinos are subatomic particles produced during nuclear reactions, such as those powering the Sun. Because neutrinos interact extremely weakly with matter, they can escape from the Sun's core and travel across space virtually unimpeded, carrying direct information about the core's conditions. Neutrino detectors on Earth, like the Super Kamiokande in Japan and the Sudbury Neutrino Observatory in Canada, are designed to capture these elusive particles. When neutrinos interact with the detecting material, usually a large volume of water or heavy water, they produce faint flashes of light known as Cherenkov radiation. Sensitive instruments detect these flashes, allowing scientists to count neutrino interactions and measure their properties such as energy and flavor. By analyzing the flux and characteristics of these solar neutrinos, scientists can test and validate models of solar fusion and energy production. The standard solar model predicts specific neutrino production rates and energy distributions for different fusion reactions in the Sun's core. Observing these neutrinos directly confirms our understanding of the nuclear reactions converting hydrogen into helium, the primary energy source for the Sun. One of the remarkable findings from neutrino detection experiments was the initial discrepancy between the predicted and observed neutrino flux, known as the solar neutrino problem. This discrepancy was eventually resolved by discovering that neutrinos can oscillate between different flavors, electron, muon, and tau neutrinos, as they travel from the Sun to Earth. This neutrino oscillation provided crucial evidence for the phenomenon of neutrino mass, fundamentally altering our understanding of particle physics. Thus, neutrino detectors provide an invaluable window into the Sun's otherwise inaccessible core, confirming theoretical models of stellar energy production and contributing to broader physics discoveries. Through continual advancements and new detectors, neutrino astronomy continues to refine our knowledge of not only the Sun, but also other astrophysical processes and fundamental particle physics. Adaptive optic systems sharpen our view of the cosmos by counteracting the blurring effects of Earth's atmosphere. When light from celestial objects travels through the atmosphere, it gets distorted by the shifting air currents and varying temperatures. This turbulence causes stars to twinkle and makes images from ground-based telescopes appear fuzzy. Adaptive optics systems achieve clarity by using a series of tiny, flexible mirrors that can adjust their shape in real time. These mirrors are controlled by computers that analyze the incoming light, detecting distortions caused by the atmosphere. By rapidly tweaking the mirrors, usually many times per second, the system effectively cancels out the atmospheric turbulence, producing a much sharper image. The technology is akin to wearing glasses that constantly adjust to keep things in focus. This allows astronomers to observe distant stars, galaxies, and other celestial phenomena with the sharpness once possible only from space-based telescopes. As a result, features such as the formation of stars in nebulas or details on exoplanets become much clearer. The use of adaptive optics has revolutionized ground-based astronomy, allowing us to probe the universe with unprecedented precision. By combating Earth's atmospheric distortions, these systems enable astronomers to uncover hidden details, advancing our understanding of the cosmos. Protecting Mars from Earth's microbes during exploration involves a meticulous process known as planetary protection. This discipline ensures that terrestrial life does not contaminate the Martian environment, preserving its natural state for scientific study and preventing any potential interference with the search for indigenous life. To achieve this, spacecraft destined for Mars must undergo rigorous sterilization procedures. Every component is meticulously cleaned and, when feasible, sterilized using heat, radiation, or chemical treatments. The assembly of these spacecraft occurs in ultra-clean facilities where air filtration systems and strict cleanliness protocols minimize microbial presence. Once assembled, the spacecraft often undergoes additional sterilization steps. For instance, parts of the spacecraft might be subjected to dry heat microbial reduction, a technique involving elevated temperatures designed to kill microorganisms. These measures ensure that even the most resilient microbes are significantly reduced. Additionally, scientists monitor and catalog microbial burdens on spacecraft, using sensitive detection techniques to assess contaminant levels. This attention to detail ensures that as humanity reaches out to Mars, we respect and preserve its pristine, potentially habitable environments, allowing for accurate and uncontaminated scientific discoveries. Asteroid mining presents a range of formidable challenges, both technical and logistical. Firstly, the sheer distance and isolation of asteroids pose significant hurdles. Reaching these celestial bodies requires spacecraft capable of enduring long-duration missions through the harsh environment of space. Navigating to a moving target many millions of miles away demands precise calculations and robust propulsion systems. Once an asteroid is reached, another challenge arises. the extremely low gravity. Operating machinery in such an environment is unlike anything on Earth. Traditional mining techniques reliant on weight and stability need to be rethought, with anchors or specialized thrusters likely required to keep equipment in place. The machinery itself must be engineered to function without breaking down in the vacuum of space, where extreme temperatures and radiation are persistent issues. Then there is the question of material processing and transportation. Extracted resources must be processed in situ or transported back to Earth or another location. Developing systems that can efficiently and safely handle this, potentially automated and without constant human oversight, is a daunting task. Additionally, the energy requirements for these processes are substantial, necessitating advanced power solutions such as solar arrays or nuclear power sources. Lastly, significant legal and ethical considerations need addressing. The Outer Space Treaty of 1967, to which many countries are signatories, states that celestial bodies are not subject to national appropriation. This presents a grey area regarding proprietary rights and obligations for asteroid mining, necessitating international cooperation and new regulations to ensure fair and sustainable use of extraterrestrial resources. Terraforming Mars to make it habitable for humans is an extraordinary concept involving immense scientific and engineering challenges. To begin, altering the Martian atmosphere is essential. Mars has a thin atmosphere primarily composed of carbon dioxide, with little to no oxygen. One idea is to release trapped gases from the planet's surface or polar ice caps to thicken the atmosphere. This could be achieved using greenhouse gases such as perfluorocarbons, which would warm the planet by retaining heat, initiating a runaway greenhouse effect that might increase atmospheric pressure and temperature. Next, creating liquid water on Mars's surface is key. Mars currently has water in the form of ice, mostly at the poles and beneath the surface. Melting this ice to create stable bodies of water involves raising the planet's temperature significantly. Once liquid water exists, it could support life and improve the feasibility of growing crops. However, preventing rapid refreezing and maintaining a stable water supply would be ongoing challenges. Another critical aspect is the generation of breathable oxygen. Methods for oxygen production include utilizing photosynthetic organisms such as algae or advanced technological processes like electrolysis of water. Once a method for consistent oxygen production is established, humans could start creating enclosed habitats with a controlled atmosphere, gradually expanding as more oxygen is produced and stored. Lastly, protecting Mars from harmful solar and cosmic radiation is vital due to its lack of a magnetic field similar to Earth's. Large-scale engineering projects such as constructing magnetic shields or creating subterranean habitats could provide necessary protection. While these steps present incredible scientific and logistical challenges, the potential for transforming Mars into a habitable world ignites the imagination and drives forward our exploration of possibilities in space colonization. Long-duration space travel imposes significant psychological challenges on astronauts, stemming from isolation, confinement, and prolonged separation from Earth. The relentless solitude can be daunting, as astronauts operate in a small, enclosed environment with limited social interaction. This isolation can lead to feelings of loneliness and constrain mental health over time, requiring robust support systems and coping strategies. Confinement in a spaceship or space station means limited physical space and privacy, which can heighten stress levels. The lack of natural environments and routine activities that are part of daily life on Earth can lead to cabin fever, where the monotony and restricted spaces amplify feelings of frustration and irritability. Maintaining a structured daily schedule and engaging in routine exercises are critical strategies used to mitigate these effects. Prolonged separation from family, friends, and the familiarities of Earth adds another layer of psychological difficulty. The knowledge that return is not possible for extended periods can weigh heavily on an astronaut's mind, exacerbating homesickness and emotional distress. Modern communication technologies, such as video calls and social media, provide some respite, allowing astronauts to maintain contact with loved ones, albeit with time delays. Another profound challenge is the constant exposure to high-risk situations. The realization of being far from immediate medical attention or emergency supports intensifies the psychological pressure. Extensive training, resilience-building exercises, and psychological support from Earth-based teams play crucial roles in preparing astronauts to manage these stressors. Despite these measures, the human psyche's response to the profound isolation and stress of long-duration space travel remains an ongoing area of research, as scientists strive to ensure that future spacefarers can maintain their mental health on extended missions. Dealing with space debris orbiting Earth is a growing concern as increasing numbers of defunct satellites, spent rocket stages, and fragments from collisions clutter the space around our planet. To tackle this issue, space agencies and organizations employ a combination of tracking, avoidance maneuvers, and innovative technological solutions. Space debris tracking is the first critical step. Organizations like the United States Space Surveillance Network use a range of ground-based radar and optical telescopes to monitor and catalog over 20,000 pieces of debris larger than a softball. This data helps predict potential collisions and warns satellite operators to take necessary actions. For smaller debris, which is harder to track but equally dangerous, simulations and statistical models estimate their distribution and movement. When a potential collision is detected, satellite operators perform avoidance maneuvers. These maneuvers involve altering the satellite's trajectory by firing onboard thrusters, ensuring it steers clear of debris paths. However, these maneuvers require fuel, limiting the satellite's operational lifespan, and must be carefully planned to avoid creating new collision risks. Innovative technological solutions are being explored to capture and remove debris. Concepts include using robotic arms, nets, harpoons, and even lasers to push debris into more manageable orbits or to burn up in Earth's atmosphere. Projects like the European Space Agency's Clear Space 1 and Japan's Aerospace Exploration Agency's Orbital Debris Removal Project are pioneering these efforts. By combining tracking, avoidance, and active removal strategies, we aim to mitigate the risk space debris poses to both current and future space missions. Quantum entanglement is a phenomenon where particles become interconnected in such a way that the state of one particle instantly influences the state of another, regardless of the distance separating them. This defies classical intuitions about the speed of information transfer, as changes seem to happen instantaneously, even across vast cosmic distances. When two particles become entangled, their properties are interlinked. For example, if you measure the spin of one entangled particle and find it to be up, the spin of the other particle, no matter how far away, will instantaneously be down. This correlation persists regardless of the distance between the particles, creating a kind of quantum handshake across the universe. This mystery puzzled Einstein, who famously referred to it as spooky action at a distance. Researchers have conducted experiments to test entanglement over increasingly larger distances. One such experiment involved entangled photons sent through optical fibers spanning over 1,000 kilometers. Even at these distances, measurement of one photon's state immediately determined the state of its twin, confirming the presence of quantum entanglement on a grand scale. Such results suggest that quantum mechanics operates in ways that classical physics cannot fully explain, hinting at deep foundational aspects of our reality that remain mysterious. While practical applications of this phenomenon, like quantum communication and cryptography, are in development, the theoretical implications challenge our understanding of space, time, and information. Quantum entanglement across vast cosmic distances underscores the interconnected and non-local nature of the quantum realm, pointing to exciting possibilities and profound questions about the universe's underlying fabric. Quantum tunneling plays a critical role in stellar fusion, the process that powers stars, including our Sun. Fusion involves light atomic nuclei merging to form a heavier nucleus, releasing tremendous amounts of energy. In the intense conditions of a star's core, hydrogen nuclei must overcome their natural electrostatic repulsion, known as the Coulomb barrier, to come close enough for the strong nuclear force to bind them together. In classical physics, overcoming this barrier would require prohibitive amounts of kinetic energy. However, quantum mechanics offers a way through this impasse. Quantum tunneling allows particles to pass through energy barriers they seemingly should not be able to surpass based on their classical energy alone. Even when nuclei do not have enough energy to overcome the Coulomb barrier directly, quantum mechanics allows for a small probability that they can tunnel through it and fuse. This phenomenon is possible because particles at the quantum level exhibit wave-like properties. These waves have a certain probability of being found on the other side of the barrier, despite the energy deficit. In the dense, hot core of a star, where countless protons are in close proximity, quantum tunneling significantly increases the likelihood of fusion events occurring, enabling the star to sustain its nuclear reactions despite the immense energy required. Without quantum tunneling, stars would need to be much hotter to sustain fusion, terms far beyond the conditions observed in the universe. Thus, quantum tunneling is indispensable, enabling stars to shine and generate the energy that supports life on planets like Earth. This quantum effect underpins the stability and longevity of stars, making it a fundamental element of cosmic structure and life cycle. Quantum effects profoundly influence the behavior of black holes, particularly near their event horizons. One of the most fascinating intersections between quantum mechanics and gravitational theory is Hawking radiation, a concept proposed by physicist Stephen Hawking. Hawking radiation suggests that black holes are not entirely black, but emit radiation due to quantum effects, leading to the gradual evaporation of the black hole over time. Hawking radiation arises from quantum fluctuations occurring near the event horizon. In quantum theory, empty space is not truly empty, but is teeming with virtual particle-antiparticle pairs that continually form and annihilate each other. Near the event horizon, the intense gravitational field can separate these pairs. One particle falls into the black hole, while the other escapes into space as radiation. This escaping particle effectively reduces the mass and energy of the black hole, a process occurring extremely slowly for large black holes, but potentially rapidly for smaller ones. Another quantum effect involves the concept of information paradox. Classical general relativity states that information swallowed by a black hole is lost forever. However, quantum mechanics insists that information cannot be destroyed. This contradiction has led scientists to explore theories such as holography. This approach suggests that all the information within a black hole could be encoded on its event horizon akin to a hologram, preserving information even as the black hole evolves. Furthermore, quantum effects could be crucial in understanding what happens inside black holes. Theoretical work on quantum gravity aims to unify general relativity and quantum mechanics, providing insights into the singularity where densities and gravitational forces infinitely increase. Many theories, such as string theory or loop quantum gravity, propose mechanisms where the quantum nature of space-time might prevent singularities from existing, significantly altering our understanding of black holes' internal structure and behavior. Through Hawking radiation, the potential resolution of the information paradox, and the quest for quantum gravity, quantum effects challenge and deepen our understanding of black holes, indicating that these cosmic objects are far more complex and dynamic than once thought. Quantum foam, also known as spacetime foam, is a concept that emerges from the intersection of quantum mechanics and general relativity. It suggests that at extremely small scales, on the order of the Planck length, which is about 10 to the minus 35th meters, space-time is not smooth and continuous, but rather chaotic and frothy. This notion was first proposed by physicist John Wheeler. In this framework, the fabric of the universe at these minuscule scales is teeming with constant transient fluctuations. These fluctuations are manifestations of the Heisenberg uncertainty principle, which asserts that certain pairs of physical properties, like energy and time, cannot both be precisely determined simultaneously. As a result, at quantum scales, particles are incessantly created and annihilated, leading to a turbulent and dynamic environment. The implications of quantum foam are profound for our understanding of the nature of space-time. It suggests that space-time at the smallest scales is far from the smooth, predictable continuum described by classical general relativity. Instead, it is a seething mass of energy fluctuations where the very fabric of the universe is constantly changing. These fluctuations could potentially have macroscopic effects, influencing phenomena such as the propagation of light and gravitational waves over vast cosmic distances. One theoretical implication of quantum foam is its role in quantum gravity, the sought-after theory that attempts to reconcile general relativity with quantum mechanics. Various approaches, such as string theory and loop quantum gravity, propose different ways this foam-like structure influences the universe. This could include the discretization of spacetime or the emergence of extra dimensions at these tiny scales. Thus, quantum foam represents a frontier of modern physics, where an improved understanding could unlock answers to some of the most profound questions about the nature of reality, the origins of the universe, and the unification of the fundamental forces. Quantum fluctuations in the early universe play a pivotal role in the formation of cosmic structures we observe today. Immediately after the Big Bang, the universe was an extremely hot, dense state where quantum mechanical effects dominated. These minute fluctuations in energy density occurred at subatomic scales due to the principles of quantum mechanics, creating tiny variations in the distribution of matter and energy. During the inflationary period, a rapid exponential expansion of the universe occurring fractions of a second after the Big Bang, these minuscule quantum fluctuations were dramatically stretched to macroscopic scales. As the universe expanded, the initially negligible variations in density grew larger, imprinted onto the expanding cosmos as perturbations in the fabric of space-time. These density fluctuations acted as seeds for the gravitational collapse that would eventually form galaxies, stars, and other cosmic structures. Regions with slightly higher density than their surroundings had a stronger gravitational pull, attracting more matter and growing larger over time. Conversely, areas with lower densities became voids, spacing out as matter gravitated towards the denser regions. Remarkably, the cosmic microwave background, a faint radiation glow left over from the early universe, provides a snapshot of these early fluctuations. Observations of the CMB by missions like COBE, WMAP, and Planck have revealed a speckled pattern of temperature variations that directly maps back to the density fluctuations from the inflationary era. These subtle variations provide crucial evidence supporting the theory of inflation and our understanding of structure formation in the universe. Quantum fluctuations in the early universe, magnified by the inflationary expansion, laid the groundwork for all cosmic structure. This bridging between the quantum world and the macroscopic universe showcases the profound interconnectedness of physical laws across different scales, leading to the diverse and complex cosmos we explore today. Quark-gluon plasmas form in neutron star collisions under conditions of extreme temperature and density. In these high-energy events, the energy and pressure are so intense that protons and neutrons, the particles that make up the nucleus of atoms, dismantle into their more fundamental components, quarks and gluons. Quarks are elementary particles, and gluons are the force carriers that mediate the strong nuclear force binding quarks together. When two neutron stars collide, their ultra-dense matter and immense gravitational forces generate unbelievable amounts of energy. During the violent merger, temperatures can soar to several trillion degrees, an environment reminiscent of the universe's first microseconds after the Big Bang. In such extreme conditions, the usual structural boundaries that confine quarks within protons and neutrons dissolve. This breakdown leads to the formation of a QGP, a state of matter where quarks and gluons exist freely rather than being bound into larger particles. Detecting and studying QGP from these cosmic events relies on observing the aftermath of neutron star collisions, typically detectable by gravitational wave detectors and telescopes that capture electromagnetic signals. Gravitational waves emitted during the collision can provide information about the star's masses and the dynamics of the merger. Subsequent electromagnetic signals, such as gamma-ray bursts and kilonovae, can help identify the creation of QGP and the formation of new elements. T. The study of QGP in neutron star collisions not only deepens our understanding of these exotic objects, but also reveals fundamental insights about the early universe's conditions. Laboratory creations of QGP, achieved in particle colliders like the Large Hadron Collider, provide a controlled context to study this state of matter. Yet, the extreme natural occurrences of QGP in neutron star collisions offer unparalleled opportunities to explore physics under the universe's most extreme conditions, pushing the boundaries of our knowledge about matter and the forces that govern it. At the center of white dwarf stars, matter exists under incredibly extreme conditions, creating a fascinating state of matter known as degenerate matter. A white dwarf is the remnants of a star that has exhausted its nuclear fuel and ejected its outer layers, leaving behind a dense core primarily composed of carbon and oxygen atoms. In the heart of a white dwarf, the pressure is so intense that electrons are squeezed into a highly compact arrangement. This immense pressure is due to the star's gravity, which attempts to compress the matter further. However, unlike typical matter, the electrons in white dwarf cores resist further compression due to a quantum mechanical principle called electron degeneracy pressure. This pressure arises because of the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state simultaneously. Under these conditions, the white dwarf's core density can be astonishingly high, often reaching levels where a single cubic centimeter of white dwarf material can weigh several tons. The atoms themselves are stripped of their outer electrons, and nuclei are packed closely together, with the degenerate electrons forming a kind of sea around them. This degenerate electron pressure is what keeps the white dwarf from collapsing under its own gravity. Eventually, over billions of years, the white dwarf will cool down and become a black dwarf, a theoretical object that no longer emits significant heat or light. However, given the current age of the universe, no black dwarfs are thought to exist yet. The study of white dwarfs offers significant insights into stellar evolution, the behavior of matter under extreme conditions, and the fascinating interplay between quantum mechanics and gravitational forces. Cosmic strings, hypothetical one-dimensional defects formed in the early universe, could potentially have a profound influence on the large-scale structure of the universe. These theoretical objects are thought to be incredibly thin, yet immensely dense, stretching across vast cosmic distances. Emerging during phase transitions in the early universe, similar to cracks forming in ice as water freezes, cosmic strings are predicted by some grand unified theories that attempt to unify all fundamental forces. If cosmic strings exist, their immense gravitational pull could influence the formation and distribution of galaxies and galaxy clusters. As these strings move through space, their gravitational influence could cause matter to clump along their paths, potentially acting as seeds around which galaxies could form. This process might explain certain large-scale patterns observed in the cosmic web, the vast network of galaxies and intergalactic matter. Additionally, the potential interaction of cosmic strings with the cosmic microwave background, the afterglow of the Big Bang, might leave distinct imprints. These strings, slicing through spacetime, could cause minute but detectable disruptions or wake patterns in the CMB, observable as temperature anisotropies. Studying these patterns could provide indirect evidence for the existence of cosmic strings and insights into the physics of the early universe. While no direct evidence for cosmic strings has been found, the concept continues to intrigue scientists because of the potential window they provide into the universe's formative moments and underlying physics. Ongoing observations, such as those from the Planck satellite, and future missions aim to detect the subtle signals cosmic strings might imprint on the cosmos, potentially unveiling a new layer of understanding about the universe's complexity and origins. Strange quark stars, often referred to simply as strange stars, are hypothetical types of compact objects believed to consist of strange quark matter. This state of matter is theorized to form under extreme pressure and density conditions, where individual protons and neutrons break down into their constituent quarks, creating a soup of up, down, and strange quarks. The formation of strange quark stars might occur through the collapse of a neutron star, an extraordinarily dense remnant of a massive star that has undergone a supernova explosion. Inside a neutron star, matter is squeezed to its most dense state short of forming a black hole. If the central density becomes high enough, the neutrons themselves could decompose into their component quarks. When this happens, strange quarks can form alongside the more familiar up and down quarks, leading to the creation of strange quark matter, a more stable state under such conditions. One key characteristic distinguishing strange quark stars from regular neutron stars is their potential density and size. Strange quark matter is thought to be even denser than the neutronium found in neutron stars. As a result, strange quark stars could be slightly smaller in radius, but with even greater central density. This extreme compactness would make them some of the densest objects in the universe. Detecting and confirming the existence of strange quark stars presents significant challenges. Observationally, they might appear similar to neutron stars, emitting X-rays and potentially having strong magnetic fields. However, subtle differences such as variations in cooling rates or slight differences in mass-to-radius ratios could hint at their presence. Future advancements in astrophysical observations and the study of high-density matter through particle accelerators may provide the evidence needed to verify the existence of these exotic celestial objects, adding a vital piece to the puzzle of stellar evolution and the behavior of matter under extreme conditions. Relativistic jets from active galactic nuclei are among the most powerful phenomena in the universe, capable of accelerating particles to near light speed. These jets are tightly collimated streams of plasma ejected from the regions around supermassive black holes that reside at the centers of active galaxies. The process begins in the accretion disk, a swirling maelstrom of gas and dust spiraling into the black hole. As material in the disk moves inward, it heats up and releases vast amounts of energy. This energy comes from the intense gravitational forces at play, causing friction and collisions that heat the gas to extreme temperatures. Magnetic fields within the accretion disk are twisted and amplified by the disk's rotation and turbulence. These magnetic fields play a crucial role in the formation and acceleration of relativistic jets. Theoretical models suggest that the magnetic fields twist tightly and reconnect, creating powerful magnetic forces that can launch material away from the black hole along its polar regions. This mechanism, known as the Blandford-Znajek process, involves the extraction of rotational energy from the black hole itself through magnetic interactions. Once the particles are launched into the jets, they are accelerated to near light speed. This acceleration is attributable to the intense magnetic fields and shock waves within the jet. As the jets extend thousands of light years into space, they carry charged particles and magnetic fields that further accelerate and collimated particles via various processes, including magnetic reconnection, shocks, and turbulence. Relativistic jets are observable across various wavelengths, from radio to gamma rays, due to the synchrotron radiation emitted by the high-speed particles spiraling around magnetic field lines. This radiation allows astronomers to study these jets and gain insights into the extreme physical processes at work near supermassive black holes. By understanding these jets, scientists probe the enigmatic relationships between black holes, their accretion disks, and magnetic fields, shedding light on the dynamics of some of the universe's most energetic events and the physics of high-energy particle acceleration. The death of the Sun, a process that will unfold over billions of years, will profoundly impact the solar system. The Sun is about halfway through its life, currently in a stable phase known as the main sequence, where it fuses hydrogen into helium. However, the solar story will take a dramatic turn in about 5 billion years. As the Sun exhausts its hydrogen fuel, it will enter the red giant phase. In this stage, the core will contract and heat up, causing the outer layers to expand significantly. The Sun will swell to engulf the inner planets, including Mercury and Venus. Earth's fate is more uncertain. It could be swallowed or might become a scorched, lifeless rock due to intensified solar radiation and solar winds stripping away its atmosphere. This transformation will drastically alter the solar system's architecture, rendering the inner regions inhospitable. After shedding its outer layers, the Sun will leave behind a hot, dense core known as a white dwarf. This remnant will cool over billions of years, no longer capable of supporting nuclear fusion. The ejected outer layers will form a beautiful, glowing shell of ionized gas called a planetary nebula, a sight that may be breathtaking from a distance in the galaxy. Over time, this nebula will disperse, enriching the interstellar medium with heavier elements. The changes won't stop there. The gravitational influence of the dying Sun will weaken, causing the orbits of the remaining planets to drift. Outer planets like Jupiter and Saturn may migrate outward, potentially altering the dynamics of any remaining asteroids and comets. In the distant future, the once vibrant solar system will become a quieter, more diffuse structure, centered around a dim white dwarf that once powered worlds. The death of the Sun will be a transformative event, marking the end of an era and the long, slow fading of the system we call home. The cosmic calendar is an illustrative concept introduced by the astronomer Carl Sagan to help comprehend the vastness of cosmic history by condensing the age of the universe, approximately 14 billion years, into a single calendar year. This metaphorical tool effectively places significant events in the universe's past and future, into a more relatable time frame for human understanding. In this cosmic calendar, the Big Bang marks the start, occurring at the very first second of January 1st. From that initial moment, the universe began its expansion and evolution. Let's journey through some notable milestones. By March, the Milky Way galaxy begins to form. The Sun and our solar system come into being around early September. Life on Earth emerges not long after, around late September. By mid-December, simple life forms evolve into more complex organisms. Dinosaurs dominate the Earth for just a few days near the end of December, only to vanish after a cataclysmic asteroid impact on December 26th. Modern humans appear on December 31st, around 11:52 p.m. Recorded human history spans just the last few seconds of the final minute, highlighting how young our civilization is in the grand context of cosmic time. Looking toward the future, key events based on current scientific predictions extend far beyond human timescales. In a few billion years, the Milky Way is expected to collide with the Andromeda Galaxy, forming a new galaxy. In about 5 billion years, the Sun will enter its red giant phase, profoundly altering the solar system. Long after the Sun becomes a white dwarf, potentially trillions of years from now, star formation in the universe will decline as the available gas is exhausted. As the universe continues to expand, galaxies will grow increasingly isolated, with dark energy accelerating this expansion. Eventually, the universe may approach heat death, where entropy reaches its maximum and all thermodynamic processes cease, leaving a dark, cold cosmos populated by remnants of stellar objects. This cosmic calendar provides context, showing not only the insignificance of human history in comparison to the grand timeline, but also offering a framework to ponder the vast, intriguing future of the universe we inhabit. Galaxies evolve over cosmic time through interactions, mergers, and internal processes that shape their structure and star formation activities. Initially, shortly after the Big Bang, the universe was a hot, dense state filled primarily with hydrogen and helium. As it expanded and cooled, these primordial gases began to coalesce under the influence of gravity, forming the first structures known as protogalaxies. Early galaxies were likely small and irregular, shaped by frequent mergers and interactions. As these protogalaxies collided and merged, they grew larger and more complex. This hierarchical model of galaxy formation suggests that today's large galaxies, like the Milky Way, formed from the amalgamation of many smaller ones. Star formation plays a central role in galaxy evolution. In the early universe, high rates of star formation led to bright blue galaxies teeming with young hot stars. Over time, as galaxies deplete their gas reserves, the rate of new star formation tends to decline. This transformation leads to a shift, where galaxies become redder and host older, cooler stars. Spiral galaxies like the Milky Way maintain star-forming regions, with their spiral arms acting as primary sites for new star production. Galaxy interactions, such as mergers and tidal interactions, significantly influence their evolution. When galaxies merge, the resulting gravitational interactions can trigger bursts of star formation and create diverse structures, including elliptical and lenticular galaxies. These interactions often result in the growth of supermassive black holes at galaxy centers, further affecting their evolution by influencing star formation and contributing to galactic stability. Throughout cosmic time, these processes, accretion, star formation, mergers, and interactions, drive the incredible diversity of galaxies we observe today, from grand spirals to massive ellipticals and irregular galaxies. Observations with telescopes like the Hubble Space Telescope and upcoming missions such as the James Webb Space Telescope continue to provide invaluable insights, allowing us to piece together the story of how galaxies, including our own, evolved over billions of years. The ultimate fate of the universe, according to current cosmological models, is primarily dictated by its rate of expansion and the properties of dark energy, the mysterious force driving this expansion. While precise predictions remain challenging, several leading theories outline potential scenarios for the universe's far future. One of the prevailing models is the Big Freeze or heat death. In this scenario, dark energy continues to push galaxies farther apart at an accelerating rate. As the universe expands, stars exhaust their nuclear fuel and cease forming new ones. Galaxies fade to darkness, leaving behind stellar remnants like white dwarfs, neutron stars, and black holes. Over trillions of years, matter becomes increasingly sparse, and the universe asymptotically approaches a state of maximum entropy, characterized by uniform, cold energy distribution and the cessation of all thermodynamic processes. Another possibility is the Big Rip. If dark energy's repulsive force, described by a parameter called the equation of state, grows stronger over time, it could eventually overcome all gravitational bonds. This scenario predicts that as the universe expands, galaxies, stars, planets, and even atomic particles would be torn apart in a dramatic cataclysmic ending. This extreme form of dark energy leads to a universe that literally rips itself apart in the distant future. A less extreme but still impactful scenario is the Big Crunch. If dark energy weakens and gravity eventually reigns, the universe's expansion could slow, halt, and reverse. This reversal would cause the universe to contract, collapsing all matter and energy back into a hot, dense state similar to the Big Bang. This cyclical model potentially sets the stage for a new universe to emerge from the ashes of the old in a dramatic rebirth. Lastly, the Big Bounce hypothesis suggests that the universe may cyclically undergo periods of expansion and contraction. After a potential Big Crunch, conditions might set the stage for another Big Bang, theoretically enabling an eternal cycle of creation, destruction, and rebirth. 2. These theories underscore our still limited understanding of the most profound questions regarding the universe's destiny. Ongoing observations, especially those aimed at understanding dark energy and the universe's large-scale structure, may eventually provide sharper insights into these potential fates, revealing the ultimate trajectory of our cosmic existence. Stellar populations in galaxies undergo significant changes over billions of years, influenced by various processes such as star formation, stellar evolution, and galactic interactions. Initially, galaxies begin their lives teeming with young, bright, and hot stars predominantly composed of hydrogen and helium, known as population 3 stars. These first-generation stars are massive and short-lived, enriching the interstellar medium with heavier elements through supernova explosions. As the galaxy evolves, these enriched materials enable the next generation of star formation, creating population 2 stars. These stars are typically older, have fewer heavy elements than younger stars, and predominantly reside in the galactic halo and globular clusters. Over time, these stars age, some evolving into red giants and then shedding their outer layers to leave behind white dwarfs, while more massive stars end their lives in supernova explosions, contributing further to the galactic chemical enrichment. Population R stars, rich in heavier elements, form in the later stages of a galaxy's evolution. These stars are found primarily in the galaxy's disk and spiral arms, where gas and dust are ample. Star formation continues, albeit at a declining rate as the galaxy ages, driven by the availability of molecular clouds and the energetics within the disk. Over billions of years, star formation may slow as gas reserves are depleted. Additionally, the evolution of stellar populations is significantly influenced by galactic interactions and mergers. Such events can trigger bursts of star formation as gas clouds collide and compress, rejuvenating star-producing regions even in older galaxies. Collisions can also redistribute stars, creating mixed populations and altering galactic dynamics. Throughout these processes, stellar populations continuously evolve. Older stars increasingly dominate as younger stars exhaust their hydrogen fuel. The galaxy's visible character changes, shifting from the blue hues of young, hot stars to the redder appearance dominated by older, cooler stars. This gradual transition reflects the broader evolutionary path galaxies follow as they mature over cosmic time, balancing star birth and death in an ever-changing cosmic landscape. Building and powering interstellar spacecraft presents extraordinary challenges, but scientists and engineers have proposed several innovative concepts for making this ambitious leap possible. Key to these concepts is overcoming the immense distances involved and ensuring the spacecraft can sustain its journey over potentially decades or centuries. One of the most promising propulsion technologies is the use of solar sails or laser sails. This method involves large, reflective sails that harness the momentum of photons. For solar sails, sunlight propels the craft, while for laser sails, powerful ground-based or space-based lasers provide the push. Projects like Breakthrough Starshot explore laser sail technology, aiming to send lightweight probes to nearby star systems at up to 20% of the speed of light. These sails would be lightweight and extremely durable to withstand the intense radiation and bombardment by interstellar particles. Another potential propulsion system is the fusion rocket. Fusion engines would use nuclear fusion, the process powering stars, to generate the immense energy required for interstellar travel. By fusing hydrogen isotopes like deuterium and tritium, a fusion rocket could achieve higher specific impulses than chemical rockets, making long-duration missions feasible. While significant engineering hurdles remain, including managing fusion reactions and handling the resulting high-energy particles, this method holds promise due to its high efficiency and energy output. Antimatter engines represent a futuristic yet highly efficient propulsion concept. When matter and antimatter collide, they annihilate each other, releasing enormous amounts of energy. Harnessing this process could propel spacecraft at significant fractions of the speed of light. However, the production, storage, and controlled annihilation of antimatter are major scientific and technical challenges yet to be overcome. For powering the spacecraft itself, several options exist. Solar panels are viable for missions within the solar system, but lose effectiveness in the interstellar void. Nuclear power sources, such as radioisotope thermoelectric generators or compact nuclear reactors, offer a reliable and long-lasting power supply to run spacecraft systems and instruments. Advances in energy harvesting, such as tapping into cosmic background radiation or using onboard batteries optimized for deep space conditions, also contribute to sustained operations. While these concepts require significant advancements in technology and deep understanding of interstellar medium interactions, they collectively sketch a roadmap toward achieving humanity's dream of interstellar exploration, advancing our capacity to reach and study distant stars. Third, constructing large-scale space habitats presents a multitude of challenges, spanning technical, logistical, and human factors. These habitats aim to provide a sustainable living environment for long-duration space missions or permanent habitation, potentially orbiting Earth or other celestial bodies like the Moon or Mars. One major challenge is life support systems. A space habitat must create a self-sustaining environment that supports air, water, food, and waste management. Closed-loop systems are essential, recycling air, water, and nutrients to support human life. This requires advanced technologies for water purification, atmospheric control, and food production, such as hydroponics or aeroponics. Maintaining these systems to ensure long-term viability without resupply from Earth is a significant technical hurdle. Structural integrity and radiation protection are also crucial. Space habitats need robust construction to withstand micrometeoroid impacts and the harsh space environment, including extreme temperatures and vacuum conditions. Additionally, radiation from cosmic rays and solar particles poses serious health risks. Effective shielding using materials like regolith, water, or specialized alloys must be integrated into the design. Some proposals include using magnetic fields to deflect radiation, albeit this requires further research and development. Logistical issues including the transport of materials and assembly in space. Constructing such habitats necessitates multiple launches, advanced robotics, and potentially in-situ resource utilization to use materials from the Moon or asteroids. Methods like 3D printing are being explored to create structures from local resources, reducing the need for transporting bulky materials from Earth. Coordinating these efforts requires precise planning and robust spacecraft capable of reliable delivery. Human factors such as psychology and social dynamics in confined, isolated environments need addressing. Long-term habitation in space requires designing habitats that support mental and emotional well-being, featuring adequate space, privacy, and opportunities for recreation. Research from the International Space Station and analog missions on Earth provides valuable insights into these aspects, helping to develop strategies to mitigate the psychological impacts of living away from Earth. Combining sustainable life support, structural resilience, logistic feasibility, and human well-being, large-scale space habitats represent a complex yet achievable frontier. As we develop these capabilities, we inch closer to realizing humanity's dreams of living beyond our home planet. Laser propulsion represents a cutting-edge concept for advancing interstellar probes, offering the potential to achieve unprecedented speeds and make voyages to nearby star systems within human lifetimes. The fundamental principle involves using intense laser beams to propel lightweight spacecraft equipped with highly reflective sails. These sails, often made from materials like graphene or ultra-thin polyamide, reflect photons from powerful ground-based or space-based lasers. Each photon imparts a tiny amount of momentum when reflected, and continuous bombardment from the laser beam provides a steady and significant thrust, gradually accelerating the probe to a substantial fraction of the speed of light. One of the most ambitious projects in this realm is Breakthrough Starshot. This initiative proposes launching small, lightweight probes weighing just a few grams. These probes would be equipped with a light sail of a few meters in size. High-powered laser arrays on Earth would focus beams on the sail, providing the sustained thrust needed to accelerate the probe to speeds of up to 20% of the speed of light. At this velocity, reaching a nearby star system like Alpha Centauri could be possible within roughly 20 years. Several technical challenges must be addressed to realize this vision. First, the development of extremely powerful and precise laser systems capable of projecting a coherent, high-intensity beam over vast distances is essential. These lasers must operate reliably for extended periods to provide consistent acceleration. Engineers are exploring phased laser arrays, which aggregate the power of multiple lasers and can be directed precisely towards the sail. The second major challenge involves creating robust, ultra-lightweight sails that can endure the high-energy laser beams without deforming or disintegrating. These sails need exceptional reflectivity and heat resistance to prevent damage from the intense radiation pressure. Additionally, accurate targeting and navigation are crucial. Even tiny imprecisions in the initial laser targeting or during flight could result in significant trajectory errors over interstellar distances. Advanced guidance systems and potentially onboard course correction capabilities will be essential to ensure that the probes reach their intended destinations. Finally, communication with these fast-moving probes is a challenge due to the vast distances and high relative speeds. Despite their small size, these probes need to have sophisticated instruments to gather data from their journeys and send it back to Earth, requiring innovations in miniaturized electronics and high-gain antennas. Overcoming these challenges could unlock the door to interstellar exploration, propelling humanity beyond our solar system and enabling us to probe the mysteries of neighboring stars and their exoplanets. Laser propulsion stands as a promising frontier, marking a bold step towards making interstellar travel a reality. Detecting Earth-like exoplanets directly involves overcoming several significant challenges due to their small size, faint light, and proximity to much brighter stars. However, advancements in technology are paving the way for more direct observations. Here are some promising technologies and methods that hold potential for achieving this goal. One of the most critical technologies is the development of space-based telescopes equipped with coronagraphs or starshades. Coronagraphs are specialized instruments that can be integrated into telescopes to block the overwhelming light of a star, allowing the faint light from surrounding planets to be observed. Starshades, on the other hand, are large, flower-shaped structures positioned in space to cast a shadow over the telescope's view of the star, effectively blocking its light while permitting the sight of nearby planets. Missions like the upcoming James Webb Space Telescope and proposed missions like the Habitable Exoplanet Observatory and the Large UV Optical Infrared Surveyor plan to incorporate these technologies for direct exoplanet observation. Another promising approach involves optical interferometry, a technique that combines light from multiple telescopes to simulate a much larger telescope with higher resolution. This method can help distinguish between the light emitted by a star and any accompanying planets. Projects such as the proposed Terrestrial Planet Finder and the Infrared Space Interferometer aim to utilize this technique to directly image and analyze Earth-like exoplanets. Adaptive optics systems are also essential for ground-based telescopes. These systems compensate for the blurring effects of Earth's atmosphere, allowing telescopes to achieve a resolution close to their theoretical limits. Large, ground-based telescopes like the Extremely Large Telescope and the Giant Magellan Telescope will use adaptive optics to improve their capabilities in detecting Earth-like planets. Additionally, Advancements in spectrograph technology play a crucial role in characterizing exoplanets. High-precision spectrographs can analyze the light reflected or emitted by exoplanets to detect specific chemical signatures and atmospheric compositions. Instruments like the Echelle spectrograph for rocky exoplanet and stable spectroscopic observations are already making strides in this area, capable of identifying key biomarkers such as oxygen, methane, and water vapor. Combining these technologies makes it feasible to progress from merely detecting Earth-like exoplanets to studying their atmospheres and potential habitability. With these advanced tools, astronomers are increasingly able to peer into the distant neighborhoods of the cosmos and explore whether other worlds like our own are common or rare, shedding light on the potential for life beyond Earth. Gravitational assists, also known as gravity slingshots, are a time-tested technique that can dramatically enhance the efficiency of space missions, particularly when exploring the outer solar system. This method involves using the gravitational field of a planet or other celestial body to accelerate a spacecraft, redirecting its trajectory and increasing its speed without using additional onboard propulsion. When a spacecraft approaches a planet, it falls into the planet's gravitational well and accelerates. As it swings around the planet, it gains some of the planet's orbital momentum. This slingshot effect allows the spacecraft to leave the planet at a higher velocity relative to the Sun than it had upon arrival. Essentially, the spacecraft borrows some of the planet's momentum, escaping the encounter with greater speed and direction adjusted for the desired trajectory. One of the most famous uses of gravitational assists was in the Voyager missions. Voyager 1 and Voyager 2 were able to visit multiple outer planets by carefully navigating through gravitational assists. For instance, Voyager 2 achieved its grand tour of Jupiter, Saturn, Uranus, and Neptune by executing a series of gravitational assists, each boosting its speed and altering its course toward the next target. To explore the outer solar system more efficiently today, new missions can utilize gravitational assists in multiple strategic ways. By planning multi-assist trajectories, missions can use multiple gravitational assists along their journey. For example, a spacecraft might first use a close flyby of Venus or Earth to gain speed before heading out to the outer planets. This multi-assist strategy can conserve fuel and reduce travel time significantly. Targeting giant planets is another effective strategy. Jupiter's immense gravitational field makes it an ideal candidate for gravitational assists. By planning precise flybys of Jupiter, spacecraft can gain substantial velocity boosts that greatly reduce travel time to distant targets such as Saturn, Uranus, Neptune, or even the Kuiper Belt and beyond. Leveraging inner planet flybys can also be beneficial. Sometimes even missions targeting outer solar system destinations start with assists from inner planets like Venus or Earth. For instance, NASA's Juno spacecraft used assist from Earth to reach Jupiter, gaining an additional 13,000 kilometers per hour of speed. Another advanced approach is interplanetary pogo sticking, which involves using a combination of smaller planetary assists to gradually build up to the necessary speed for deep space missions. This method can optimize the trajectory and reduce the mission's reliance on heavy propulsion systems. Advanced mission planning software and real-time trajectory adjustments allow precision in executing these assists. By leveraging gravitational assists thoughtfully, missions can reach the outer solar system more efficiently, unlocking new frontiers in planetary science, astrophysics, and potentially even deep space exploration. Through this elegant blend of celestial mechanics, spacecraft effectively harness the natural gravitational ballet of the solar system to explore its farthest reaches. The entry of a rogue planet into our solar system would be an extraordinary and potentially disruptive event. Rogue planets, or interstellar planets, are those not bound to any particular star system, wandering the galaxy alone. If one were to venture close to or into our solar system, several outcomes could unfold depending on its trajectory, size, and speed. Initially, as the rogue planet approaches, it would likely first affect the outer regions of the solar system. The gravitational influence of such a planet could cause perturbations in the orbits of distant objects like those in the Kuiper Belt and the scattered disk, potentially redirecting some of these smaller bodies toward the inner solar system. This could increase cometary activity and the rate of meteor impacts on the planets, including Earth. As the rogue planet moves closer, it could have dramatic gravitational interactions with the gas giants. For instance, if it passed near Jupiter or Saturn, its gravitational influence could significantly alter their moon's orbits or potentially even destabilize the gas giants' own trajectories. These interactions might also fling some of the moons out of their orbits or capture new moons, changing the dynamics of these complex systems. In the worst-case scenario, if the rogue planet had a very close encounter with a planet like Earth or Mars, the gravitational forces could result in severe orbital disturbances. Even without a direct collision, the rogue planet could alter Earth's orbit, pushing our planet closer to or farther from the Sun, leading to drastic climate changes. Tidal effects could significantly increase geological activity, such as earthquakes and volcanic eruptions. Changes in Earth's rotation or axial tilt could greatly affect seasons and weather patterns. If the rogue planet were to settle into a stable orbit within the solar system, it could eventually become integrated without causing catastrophic disruptions. Alternatively, if it passed through the solar system and continued on its journey, the disturbances it caused would gradually settle over time, although its passage might leave long-lasting effects on the solar system's structure and dynamical evolution. Scientific detection and tracking of such an intruding rogue planet would be critical to predicting and mitigating its potential impacts. Understanding its characteristics and trajectory would enable astronomers to model possible outcomes and devise strategies to protect human assets and mitigate risks. Overall, while the entrance of a rogue planet into our solar system is a rare and hypothetical event, its potential to reshape celestial mechanics and planetary environments highlights the importance of continued observations and advancements in our understanding of such cosmic phenomena. Potentially hazardous asteroids, defined as those that come within about 7.5 million kilometers of Earth and are large enough to cause significant regional damage if they impact, pass close to our planet relatively frequently in astronomical terms. The frequency of these encounters depends on various factors, including the size and orbit of the asteroids. Smaller PHAs, ranging from a few meters to tens of meters in diameter, pass close to Earth more often. These smaller objects might come within the lunar distance, roughly 384,000 kilometers, several times each month. However, most of these would burn up in the Earth's atmosphere upon entry, posing minimal threat to the surface. Medium-sized PHAs, with diameters of a few hundred meters, pass close to Earth less frequently but still regularly. Such asteroids could be near the Earth's orbit roughly once every few years to decades. An impact from an asteroid of this size could cause substantial regional devastation, similar to the Tunguska event in 1908, which leveled around 2,000 square kilometers of forest in Siberia. Large PHAs, greater than 1 kilometer in diameter, are rarer, and their close approaches occur on timescales of centuries. Asteroids of this size possess enough energy to cause global consequences, affecting climate and potentially leading to mass extinctions, akin to the Chicxulub impact that contributed to the extinction of the dinosaurs about 66 million years ago. NASA and other space agencies actively track PHAs through programs such as the Near-Earth Object Observations. These initiatives use telescopes and radar to monitor and characterize the orbits of near-Earth objects, predicting potential threats years in advance. As of now, there are no known PHAs on a collision course with Earth in the foreseeable future, but continuous monitoring is essential to ensure timely detection and response. With advancements in telescope technology, data collection, and computational models, our ability to detect, track, and predict the trajectories of potentially hazardous asteroids has significantly improved. This ongoing vigilance is crucial for planetary defense, allowing for potential mitigation strategies such as deflection missions or evacuation plans to be developed should a credible threat be identified. A nearby gamma-ray burst could have profound and potentially catastrophic consequences for Earth. GRBs are intense and extremely energetic explosions thought to result from specific cosmic events such as the collapse of massive stars into black holes or neutron star mergers. While these bursts typically originate from distant galaxies, if one were to occur relatively close to our solar system, the effects could be severe. One of the primary dangers of a nearby GRB is the intense burst of gamma radiation that it emits. If Earth were in the direct line of this radiation, the atmosphere's outer layers would absorb a significant amount of energy, leading to a cascade of chemical reactions. This could result in severe consequences. Gamma radiation could break down nitrogen and oxygen molecules, producing nitrogen oxides. These compounds have the potential to severely deplete the ozone layer, which protects life on Earth from harmful ultraviolet radiation. Even partial destruction of the ozone layer could increase UVB radiation levels at the surface, leading to higher rates of skin cancer, cataracts, and other health issues. It could also damage ecosystems, particularly phytoplankton in the ocean, which are crucial for the marine food chain and carbon cycling. The presence of nitrogen oxides can lead to the formation of smog and acid rain, which could have adverse environmental effects. Additionally, the secondary effects of increased ultraviolet radiation could alter atmospheric dynamics and weather patterns, although the exact mechanisms would require further study. While the atmosphere would absorb most of the direct gamma rays, secondary radiation could still reach the surface, potentially causing radiation sickness in humans and other terrestrial life forms, depending on the burst's proximity and duration. Historical evidence suggests that past mass extinction events could be linked to such cosmic occurrences. A sufficiently close and intense GRB could lead to a biological crisis, significantly impacting biodiversity and potentially causing a mass extinction event. Fortunately, GRBs within the Milky Way galaxy are exceedingly rare, and the probability of one occurring close enough to Earth to cause such effects is very low. Current astrophysical research estimates that a deadly GRB striking Earth is a rare event, likely happening only once every few 100 million years. To manage such risks, ongoing astronomical observations and studies help improve our understanding of GRBs, including their origins, frequencies, and potential threat to Earth. This knowledge aids in preparing for and mitigating the impacts of various cosmic hazards, ensuring that we stay vigilant in protecting life on our planet from these extreme, albeit rare, extraterrestrial events. Planetary impacts play a crucial role in shaping the evolution of solar systems, influencing their physical structure, composition, and habitability. These cataclysmic events, ranging from the collision of small meteoroids to massive planetary-scale impacts, drive dynamic processes that significantly alter celestial bodies and their environments. In the early stages of solar system formation, impacts were frequent and transformative. During this period, known as the heavy bombardment, protoplanets and planetesimals collided frequently as they coalesced from the protoplanetary disk of gas and dust. These collisions contributed to the accretion of planetary bodies, helping to form larger planets from smaller building blocks. Through these high-energy impacts, planets grew in mass and differentiated into distinct layers, such as cores, mantles, and crusts. The Moon's formation is a striking example of the impact's profound effects. Current leading theories, like the giant impact hypothesis, suggest that the Moon resulted from a colossal collision between the early Earth and a Mars-sized body named Theia. The debris ejected from this impact eventually coalesced to form the Moon. This event not only shaped the Earth-Moon system, but also influenced Earth's tilt and rotation, which have critical implications for the planet's climate and the stability of its seasons. Impacts have also played a significant role in the geological and atmospheric evolution of planets. On Earth, impacts have periodically reset the biological clock, as evidenced by events like the Chicxulub impact, which is linked to the mass extinction that wiped out the dinosaurs around 66 million years ago. These events can cause drastic changes in climate, trigger volcanic activity, and even catalyze the emergence of new evolutionary pathways by creating unique niches and eliminating dominant species. Furthermore, planetary impacts are essential in delivering essential volatiles and organics. The theory of panspermia suggests that impacts could transport organic molecules or even microbial life between planets, potentially seeding life. During the early bombardment phase, impacts likely delivered significant amounts of water and organic compounds to Earth and other terrestrial planets, contributing to the conditions necessary for life to arise. In modern times, smaller-scale impacts continue to shape planetary surfaces, creating craters, altering landscapes, and impacting atmospheric conditions. Studying impact craters on bodies like the Moon, Mars, and Mercury provides valuable insights into the history and evolution of the solar system. Planetary impacts are a fundamental force in sculpting the architecture and development of solar systems. They drive the formation of planetary bodies, create moons, influence geological and atmospheric conditions, and potentially play a role in the origin and distribution of life. Understanding these processes allows us to piece together the complex history of our solar system and offers clues about the evolution of other planetary systems in the universe. The anticipated collision between our Milky Way galaxy and the Andromeda galaxy, expected to occur in about 4 billion years, is a monumental event in the universe's history. This cosmic dance is already in motion, as Andromeda and the Milky Way are moving towards each other at speeds of about 110 kilometers per second. While such galactic collisions may sound catastrophic, the actual effects on solar systems within these galaxies are more nuanced and fascinating. As Andromeda approaches, the first noticeable effect would be the gradual alteration of the night sky visible from Earth, with Andromeda appearing larger and more prominent over millions of years. Eventually, the gravitational forces between the two galaxies will pull them together, initiating the collision. However, because galaxies are primarily vast spaces with massive distances between stars, direct stellar collisions are surprisingly rare. Instead, stars and planetary systems are more likely to be affected by gravitational interactions. These interactions can cause various phenomena. The collision will compress interstellar gas and dust, triggering intense periods of star formation known as starbursts. These regions will give rise to new stars and potentially new planetary systems, shining brightly as new stellar nurseries. While direct collisions are unlikely, the gravitational forces can alter the orbits of stars and planetary systems. Some systems may be ejected into intergalactic space, creating rogue stars. Others might be rerouted into new orbits around the merged galaxy's core or different regions of it. Both the Milky Way and Andromeda have supermassive black holes at their centers. As the galaxies converge, these black holes will eventually spiral towards each other and merge, releasing tremendous energy in the form of gravitational waves. The final stage of the collision involves the merging of the two galaxies into a single larger elliptical galaxy, often referred to as Milkomeda or Milkdromeda. This new galaxy will have a different structure and star formation rates compared to the separate Milky Way and Andromeda. Over subsequent billions of years, the merged galaxy will stabilize and settle into a new configuration. For our solar system, the event's immediate impacts might be relatively minimal. While the night sky would change dramatically with a more crowded and dynamic celestial vista, the odds of our solar system being ejected or significantly disrupted are low. Nevertheless, gravitational forces could alter our position within the galaxy, possibly shifting the solar system closer to or further from the galactic core. In sum, while the collision between the Milky Way and Andromeda is a distant yet inevitable event, it promises to be a spectacular process reshaping the local universe. It highlights the dynamic and ever-evolving nature of cosmic structures, embodying both the destructive and creative forces that govern the universe's grand tapestry. Oumuamua, an interstellar object detected in our solar system in October 2017, has intrigued scientists with its mysterious properties and origins. Named Oumuamua, which means scout or messenger in Hawaiian, This object is the first known visitor from another star system, offering a rare opportunity to study an interstellar relic. The nature of Oumuamua is fascinating due to several unusual characteristics. First, its velocity and trajectory indicated that it did not originate within our solar system. Instead, it is a visitor from interstellar space, likely ejected from another star system. Its high speed and hyperbolic trajectory suggested it was passing through the solar system and would not return, showing it was not gravitationally bound to the Sun. Another notable feature of Oumuamua is its peculiar shape. Observations indicated that it is elongated, with a length-to-width ratio of about 10:1, much like a cigar or a flattened pancake. This is dramatically different from most asteroids or comets, which tend to be more rounded or irregularly shaped. The exact dimensions are estimated to be roughly 800 meters long and 80 meters thick. Oumuamua's composition and surface properties also raised questions. Initially, it was thought to be a comet due to its interstellar origin. However, it lacked the characteristic coma or tail that comets display when they approach the Sun and begin to sublimate. Instead, Oumuamua exhibited unusual non-gravitational acceleration as it moved away from the Sun, possibly indicating outgassing of volatile substances that were not easily visible. Various hypotheses have been proposed to explain Oumuamua's nature. One theory suggested it could be a fragment of a larger body, possibly crafted by a collision in its home system. Some researchers speculated it might be composed of a material that behaves differently under solar heating. Alternatives ranged from being an unusual asteroid to an icy body with a protective organic-rich crust preventing sublimation. A more speculative idea proposed by some scientists, including those at Harvard University, was the possibility that Oumuamua might be an artificial object, perhaps a light sail or probe from an advanced extraterrestrial civilization. However, most in the scientific community consider this notion less likely, while emphasizing the need for further study. The brief period. Oumuamua was observable limited our ability to fully understand its properties. As such, it underscores the importance of quick response and robust observation strategies in studying transient interstellar visitors. Telescopes and other observational instruments continue to search for similar objects, which could provide more clues and contribute to understanding the processes shaping the cosmos beyond our solar system. The discrepancy between the observed abundance of lithium in the universe and the amount predicted by models of Big Bang nucleosynthesis is known as the lithium problem. Big Bang nucleosynthesis, the process of forming light elements in the early universe, predicts that lithium, along with hydrogen and helium, should have been produced in specific amounts. However, when we observe old stars and primordial gas clouds, they appear to contain significantly less lithium than expected. Several hypotheses have been proposed to explain this discrepancy. Stellar processes might be responsible for depleting lithium in their atmospheres through internal mechanisms. Stellar models suggest that lithium can be destroyed in the hot interiors of stars, where convective movements may bring lithium to hotter interior regions to be burned and turned into other elements. This is especially plausible in older stars, which might have reduced lithium levels in the observable surface layers. However, even after accounting for stellar depletion, some discrepancies remain. The rates of nuclear reactions that produce and destroy lithium during Big Bang nucleosynthesis might differ from initial estimates. Updated models and experimental results concerning these reaction rates could refine predictions and align them more closely with observations. Yet, many studies suggest that uncertainties in reaction rates alone cannot fully explain the discrepancy. Astration, the cycling of material through multiple generations of stars over time, could lead to lithium depletion. As stars form, evolve, and expire, they might gradually consume and reprocess lithium. However, this does not fully account for the lithium deficit in the oldest, most metal-poor stars, which should reflect the primordial abundances of elements. Alternative scenarios in cosmology or astrophysics might also be at play. For instance, early stars, known as population 3 stars, might have processed lithium differently due to their unique properties. However, there is little direct evidence to support this, as these stars have not yet been observed. The lithium problem has led some researchers to consider new physics beyond the standard model. Possibilities include modifications to particle physics that could affect Big Bang nucleosynthesis or the existence of unknown particles or processes that influence element formation. Adjusting the abundances or decay rates of certain particles in the early universe could theoretically impact lithium production. Resolving the lithium problem requires advanced observational techniques and more precise theoretical models. Improving our understanding of stellar evolution, refining nuclear reaction rate measurements, and exploring non-standard cosmological models all contribute to this ongoing investigation. Until a definitive solution is found, the lithium problem remains an intriguing puzzle, highlighting the complexities of our universe and the limits of our current scientific knowledge. Fast radio bursts are one of the most intriguing astrophysical phenomena, marked by extremely brief but intense bursts of radio waves emanating from deep space. Despite the recent surge in detecting these events, their exact origins remain a topic of active research and considerable debate. A variety of potential sources and mechanisms have been proposed to explain these enigmatic signals. One leading hypothesis attributes FRBs to highly magnetized neutron stars known as magnetars. Magnetars possess immensely powerful magnetic fields, and it is theorized that the sudden release of magnetic energy on these stars can generate intense radio bursts. This idea gained traction with the discovery that some FRBs repeat, hinting at a persistent rather than one-time astronomical source. Flares from magnetars fit this bill well. Another possibility involves neutron star mergers or collisions. When two neutron stars collide, they could produce a short-lived but powerful burst of radio waves as part of the cataclysmic event. This scenario aligns more closely with the observed non-repeating FRBs, suggesting different types of FRBs may have different origins. Beyond neutron stars, other proposed mechanisms include various intriguing possibilities. Interactions involving black holes, such as the accretion of matter or the merging of black holes with other compact objects, could theoretically produce FRBs. Energetic processes surrounding supernovae and their remnants might generate the conditions necessary for these high-energy radio bursts. Some researchers have speculated that interactions between ordinary matter and dark matter could be responsible, although this remains highly speculative and unproven. Although more speculative and less favored by the scientific community, the notion that FRBs could be artificial signals from advanced extraterrestrial technologies has been posited as a possibility. This idea captures imaginations but lacks concrete evidence. Observations by powerful radio telescopes like the Canadian Hydrogen Intensity Mapping Experiment and the Australian Square Kilometre Array Pathfinder have significantly advanced our understanding of FRBs. These instruments have detected numerous FRBs, pinpointing their origins to specific galaxies, often billions of light-years away. By analyzing the dispersion and polarization of the radio waves, astronomers can infer properties about the space the bursts have traveled through, providing clues about their origins. Continued monitoring and enhancement of observational capabilities are crucial. With forthcoming telescopes such as the Square Kilometre Array, scientists expect to capture many more FRBs and further refine models to pinpoint their sources and mechanisms. Despite the enigmatic nature of FRBs, the scientific community is steadily gathering data that promises to eventually shed light on these enigmatic cosmic signals, adding another layer to our understanding of the universe's complexities. Intermediate mass black holes occupy a middle ground between stellar mass black holes, which are typically formed from the collapse of massive stars and range from a few to a few dozen times the mass of the Sun, and supermassive black holes found at the centers of galaxies and containing millions to billions of solar masses. despite numerous detections of both stellar mass and supermassive black holes, finding evidence for IMBHs with masses between 100 to 100,000 solar masses has proven elusive. Several factors contribute to this apparent shortage. One reason is the observational challenges. IMBHs are harder to detect due to their subtle signatures compared to their more massive counterparts. Supermassive black holes produce prodigious amounts of radiation, especially as they accrete matter from surrounding galactic centers, making them relatively easy to spot. Stellar mass black holes often reveal themselves through interactions with companion stars in binary systems. In contrast, IMBHs might not have such clear markers, especially if they are located in less dense regions of galaxies or in isolated environments where less matter is available for accretion. The formation mechanisms of IMBHs remain uncertain, with various theories proposing how these elusive black holes might come into existence. In dense star clusters, runaway collisions of massive stars could possibly form IMBHs. However, such conditions are rare, and the resulting black holes might then be ejected from the cluster, making them hard to find. Another hypothesis suggests that very massive population 3 stars, the first generation of stars formed after the Big Bang, could collapse directly into IMBHs without going through a supernova phase. Observing the remnants of these stars is challenging due to their potential scarcity and the vast distances involved. Some models suggest that smaller black holes might grow into IMBHs by accreting gas or merging with other black holes. However, this process could be slow and inefficient, reducing the number of IMBHs presently observable. Recent efforts have provided some tantalizing hints of IMBHs. The detection of gravitational waves from binary black hole mergers by observatories like LIGO and Virgo has started to probe the mass range between stellar and supermassive black holes. For instance, collisions resulting in black holes with masses in the intermediate range yield critical data. Observations of ultraluminous X-ray sources in nearby galaxies also suggest the possible presence of IMBHs, as their luminosities exceed what is expected from typical stellar mass black holes. Future missions and observatories will enhance our ability to detect and understand IMBHs. Space-based gravitational wave detectors like the Laser Interferometer, Space Antenna, and advanced X-ray telescopes could provide new insights into the environments and formation processes of these enigmatic objects. The apparent shortage of IMBHs highlights a significant gap in our understanding of black hole formation and evolution, providing an exciting frontier for astrophysical research. As observational techniques improve and theoretical models refine, we can expect to learn more about these elusive objects and their role in the cosmic landscape. The true nature of dark energy remains one of the most profound mysteries in cosmology. Dark energy is hypothesized to be the driving force behind the accelerated expansion of the universe, a phenomenon first observed in the late 1990s through studies of distant Type Ia supernovae. Despite its significant impact on the cosmos, dark energy's exact properties and origins are not well understood. Dark energy is characterized by its uniformly distributed pervasive presence throughout space, consistently influencing the universe's expansion rate. Several theories have been proposed to explain dark energy, each tackling different aspects of this enigmatic force. The cosmological constant, proposed by Albert Einstein as a modification to his equations of general relativity, represents a constant energy density filling space homogeneously. In modern terms, it is viewed as a vacuum energy inherent to space itself, exerting a repulsive force that counteracts gravity, leading to the accelerated expansion of the universe. Although the cosmological constant provides a simple and compelling explanation, its theoretical value, derived from quantum field theories, is vastly larger than what is observed, creating a significant discrepancy known as the cosmological constant problem. Quintessence, unlike the constant energy density of the cosmological constant, postulates a dynamic, evolving field. This scalar field varies over time and space, potentially explaining the universe's changing expansion rate. However, identifying the precise nature and behavior of this field remains challenging, and there is no direct evidence for its existence. Some theories suggest that general relativity, our current understanding of gravity, might need modification on cosmic scales. Alternative theories, such as FR gravity and brain-world models, propose that changes in gravitational dynamics could account for the observed acceleration without invoking dark energy as a separate entity. These theories aim to provide a unified framework for both cosmic acceleration and other gravitational phenomena. Other models explore the possibility that dark energy interacts with other components of the universe, such as dark matter or massive neutrinos, affecting the expansion rate. These interactions could lead to varying effects over time, offering potential explanations for the observed acceleration. More speculative theories, such as those derived from string theory and the holographic principle, propose that properties of the universe, including dark energy, can be understood as emerging from a higher dimensional framework. These ideas remain highly theoretical and are at the frontier of current physics research. Despite various propositions, definitive evidence for any specific model remains elusive. Observational efforts are ongoing, with projects like the Dark Energy Survey, the Euclid Space Telescope, and the upcoming Nancy Grace Roman Space Telescope aimed at mapping the cosmic expansion with greater precision. These projects study the large-scale structure of the universe, the cosmic microwave background, and the behavior of distant supernova to constrain the properties of dark energy. Dark energy is a mysterious force driving the accelerated expansion of the universe. While several theories attempt to explain its nature, from the cosmological constant to quintessence and beyond, the true essence of dark energy remains one of the most profound puzzles in physics. Continued observations and theoretical advancements are crucial to unlocking this enigma and deepening our understanding of the universe's fundamental structure. What do you believe exists out there in the vast universe? Are we truly alone, or could there be other life hiding from us? Let us know your thoughts in the comments below. Thanks for watching.